All right, welcome back. We're on the next lecture, so hopefully you have had time to recover from our diode discussions. So that was pretty long. We went through a lot of material, a lot of theory and hands-on experiments. So we're going to do the same here with transistors, but let's take a look back and think we've gone over resistors, we've gone over capacitors, inductors, LEDs, diodes now, transformers. We know Ohm's law, we know digital, analog, what the words mean at least, and we're really making good progress here. So after we get done with transistors, we're going to have a good set of building blocks to make a lot of really cool circuits. So let's see. So what we're going to do is we're going to do some theory, and then we're going to jump in. And I know I say this always. We're going to do theory, and then we're going to do the actual some experiments with transistors and play around with them. All right. So and this is, and I've thought about this. This is a really hard subject to teach in kind of a simple way. You really do need to dig down and do the math and do the physics and take time with it. But I want to show you at least a general overview of what's going on with the physics, something like we did with the diodes, and I think that'll be good enough. A really simple equation that models how we're going to use a transistor, and then later, as we go down further lectures, we'll kind of add to it a little bit. And of course, you can always on your own go and Google and look online and look for more advanced material. There's plenty of it. But what my goal always is to try and give you a working knowledge and hands-on technique so that you can actually build something and work with me as we build something and see the thought process. All right, so take a look at the screen here. So let's get right into this. All right, so we've got the transistor. So the transistor, and we're going to be talking about the bipolar junction transistor, BJT it's called. And this is a three-layer device, and you're going to find two different kinds of transistors, which are the most common, and that's called a PNP and an NPN transistor, and it basically is talking about the doping. So PNP or NPN, it's just like the diode, which is just P and N. All right, and these transistors have three leads, and one is called the base, the other is called the emitter, the other is called the collector. All right, and before, so let's take a quick look. Let's take a quick look on one of the other bench cameras. I want you to actually see this. Okay, so here we have a 3906, and this is a PNP transistor. And we're going to look at it. We're going to look at a bunch of these in a little while when we do the actual experiments. But you can see it has three leads, and starting from the left, typically, starting from the left, we would have emitter, base, and collector. All right, and then something else about, and of course, this is just one package of a transistor. There are many packages, but this is kind of the through-hole package. You see, it's kind of a half semicircle with a little bit extra there. All right, and anyway, so to the left, starting to the left, we have emitter, then the center is base, and then to the right is the collector. And this is a PNP. And an NPN transistor looks identical. So let's see if I can find one real quick. And here we go. Here is a 2222, and this is an NPN. And this one's just labeled differently. It doesn't have the emitter base collector labeled on there. And this is a Fairchild. You can see the F. All right, so but that's what a transistor looks like. That's the size of it, of a through-hole transistor. All right, and of course there's surface mount transistors that would fit in, the size of a grain of salt. Well, actually nanometers, right? Transistors, if you look at a Intel processor or a GPU, we're talking about nanometer features. That's how big transistors are these days. Okay, all right. Okay, so we're going to do this from both ends. We're going to talk about things. So looking at the screen here and looking at this figure that I have up on the screen. All right, so the two different kinds of transistors, we have an NPN transistor and a PNP transistor. And again, the NPN, we have a collector, we have a base, we have an emitter. And here's how they're doped, right? So we have semiconductor material like a silicon, and then it's doped. So we get N, we get P, we get N to make the collector base emitter over in the NPN. And then over in the PNP, it's the exact same thing. It's just opposite. So we've got collector base emitter, same thing, PNP. The symbols are hard to remember and which one goes which way. So basically the NPN points out and the PNP points in. One way is you can remember this as the P points in, and it points into the this little cross area here. So anyway, until you remember it, you may draw them backwards. Anyway, so we've got base, we've got collector, we got emitter. So we've got three different contacts here. And the question is, how does this thing work, right? All right, looking at a cross section over here to the left, this is a very crude rendition of what a transistor might look like as it's actually etched into silicon. And so we have, so all this would start off being silicon, and then it would be doped and then etched and so forth. And the whole process of building semiconductors is fascinating, and there are many classes and many books on it, which you might want to take a look at, or some videos online. In any event, so we've got the collector here, and then we've got this metal contact, so that's how we make a contact to the collector. Then we have the base, all right, and then we have the emitter, and then again, there's metal, there's metal, there's metal, and then the insulator is a silicon oxide, or silicon dioxide is the insulator, and that just grows. You add oxygen, and you can get this silicon oxygen insulator, which is a great insulator that's used in semiconductor fabrication. So this is kind of what it looks like, but that's not really telling us much. This is a more telling pictorial right here, and the reason why is because clearly this looks like it's two diodes, right? It's just one diode in this direction, another diode in this direction, same thing here. So the question is it just two diodes? And the answer is yes, right? But they're doped in a special way to give the three-layer device different properties than just two diodes that would be connected back to back. And so later, you'll learn that there are many kinds of semiconductor devices that have many layers. There's a 3-layer, 4-layer. There's all kinds of crazy configurations of semiconductor devices. And how they get the different properties is by doping them in a different way. So they may have the N and the P's like diodes, but they're not diodes strictly speaking. Okay, so let's continue on here. All right, so and I'm gonna do some drawing to really help clarify all this stuff. So to get a transistor to work, what a transistor more or less is, it's an electronic switch. It's a current-controlled switch. All right, and what we do is we push current or pull current into the base, and then that turns on the collector circuit. So we have in this top part of the top part of this figure here, we've got a transistor, and this is a PNP. And in this case, we forward bias this. So here's the emitter and here's the base. So we forward bias the base emitter junction here, all right, and we call this current I sub E. So this is this current here. Then we reverse bias the base collector junction. So this is how you kind of set this up. And then what happens is you're going to get current coming out of the base, right, or sinking current out. This transistor will turn on, and then current will flow in this secondary circuit. So the whole idea is you could think of as the base is the control for this electronic switch, this current controlled switch, all right? And as we change the base current, this current here in this collector emitter circuit changes dramatically. It's amplified. All right, and how that process works we'll get to in a minute. But so that's the point. So basically we put in a little bit of current or pull out a little bit of current out of the base, and that causes a lot of current to flow in the emitter collector circuit here. All right. So now one thing that I want to do is the PNP transistor and the NPN are identical other than signs and the direction that things flow. So we're going to talk about the NPN mostly for our experiments, and this is kind of the more common transistor people like to use. It's a little easier to understand. Okay, so again, in this configuration, so now we have an NPN transistor. the here's the base, here's the emitter, here's the collector. So we forward bias the base emitter junction, and then the base collector junction is reverse biased. Okay, so what this really looks like is we put a positive voltage here on the base, and we drive current into the base. As we drive current into the base, it starts turning this switch on. This transistor starts getting turned on, and a current starts flowing from this other source here, positive current we're talking about, conventional current, flows through this base emitter, through this collector emitter junction, and then back to the sources here. All right, so again, a small amount of current is used to control current in the secondary part of the circuit. All right, and when you look at it like this, it's a little hard to figure out what's going on as far as the physics are going. So that's what we're going to take a look at right now, and kind of see exactly what's going on, so that we can kind of understand a little bit better when we use this model. All right, so let's go ahead and let's go do some drawing now. All right, so what I'm going to draw is I'm going to draw an NPN transistor, but I'm going to draw it at the kind of physics level here, so we can kind of see what's going on. So let's do some color coding here for once. So let's say that N material is red. Okay. All right. So N material is red. Okay. So there's one N, and then here's a P region. All right. And we'll just double cross those. And then here's our other, and these are totally connected together, right? They've been fused. I'm just drawing them like this. Okay, so we've got our N, we've got our N, and we've got our P here. All right, and so now let's draw what's in here. So these started off as being silicon, and we've doped them. All right, and we've made this this section right here, which in this case, let's go ahead and let's call this the emitter. All right, so we're going to call this the emitter. All right, and then this would be the collector. All right, and then this blue guy in the middle is the base. Okay, so now let's go and let's put our charge here. So all of these little red dots are free electrons. So we've doped this with, say, a pentavalent material like phosphorus, right? So we've got an excess of charge here, negative charge, electrons. Same thing over here. All right, let's draw these in here. And what's interesting is I'm going to just tell you a little bit of what makes things different is the emitter is heavily doped. So this is heavily doped. So really what it looks like is this. It's got way more free charge than the collector does. Okay, so let's draw those in there to represent that. So you can see the density of these free charges is much higher. So this is heavily doped. All right. Now, the base is doped as well, and it's doped so that it's got positive charge or holes. All right. Okay. So now let's mark some things here. So this is heavily doped, and the collector is lightly doped. So that's why you just can't use two diodes and put them back to back. All right. They have to have this doping, and the manufacturers control this doping very, very carefully. Okay, so we've got our NPN transistor here, and what we want to do is let's forget about this half of things for now, and let's just talk about the left half of things. So let's go ahead and see if we can forward bias the base emitter transistor diode here. Okay, so we've got a diode here, right? P and N. All right, so we remember if we go here and we connect this, and let's connect this to a positive battery, all right? And you could put a resistor in here to limit current, right? So we can put that, that's not going to hurt anything. All right, and these contacts are, the metal contacts that we saw in the figure above. Okay, so what happens when I do this is that this is a diode, right? And now you can see that we forward bias this diode. And because we forward bias the diode, what's going to happen is this region in here, right, this P, we've got two different depletion regions, don't we? All right, we've got these two different depletion regions, and I'm going to draw them in a kind of orange to represent what's happening. So at these interfaces where the emitter touches the base and the base touches the collector, you've actually got these depletion regions, and that's what happens at P and N junctions, right? And so what happens is you've got a bunch of negative charge here and positive charge. So some of the positive charge goes over here, and the negative charge goes over there, and it comes to an equilibrium, and you've got this potential energy gap, right? Okay. And we've got these on both sides. And so what we're trying to do right now is we are trying to get some current to flow over in this part of the circuit and see maybe if something magical happens. So we're applying forward bias, a positive, and let's make sure here we got positive, we got negative, right? And here's R. And we're applying a positive voltage here. And what we're trying to do is we're trying to inject current here, right? And I'm going to call this I sub B. All right. And the moment that we bias this enough, and this battery, we'll call this VV, V bias, the moment that this is large enough, it's going to start turning on this diode right here. Forget about this diode, but it's going to start turning on this diode. This depletion region is going to, the width is going to get less and less and less. And then what's going to happen is charge is going to start moving. So holes are going to start moving from the base into the emitter, and electrons from the emitter are going to start moving into the base. Okay. Now, what I want to do now is I'm going to switch from talking about conventional current, and I want to talk about electron current. It just makes it a little bit easier. So this is what we're doing, all right? This is what we're doing, but let's just talk about things in terms of electrons. All right. So as we make this this depletion region smaller and smaller by forward biasing it, these electrons over here are, some electrons are coming in from this side of the battery, right? So we're getting some electrons moving in here, right? And this is getting really crowded. The depletion region is getting smaller and smaller because the voltage, the bias we're applying to the base emitter junction. And then so what starts to happen is we start getting current flow, right? So we start getting electrons moving over here, right? And they're moving over here and they're recombining with holes, all right? And the holes are moving to the left as that's happening, right? So we're getting our current flow, right? We're getting our current flow over here. Now, so this is all good over here. So now the question is, what can we do with this side over here? So now that we have this action occurring over here in the base and the emitter area, so now what can we do over with the collector area? So take a look here. So now if we go and we take a, let's draw it from here. If we take another battery here, and I'm going to draw it up here, it'll make it a little bit easier. And hopefully I'm going to draw this in the right orientation. All right. That's why it's always nice to have things pre-done, but again, I like to do things kind of on the fly so we can see what's going on. All right, and we're going to call this V sub C or V sub CC, and we'll just call this R sub C, and I'm just going to call this R sub base. Okay, so now in this situation, now what we have here is we've got a current, right? A conventional current here, this I sub B, which is a voltage we've applied to the base, to the emitter here. This is causing this diode to become turned on. So the diode is getting turned on. Now we've over here, right, at the collector here, up at the collector, we've got a positive voltage, another positive voltage, and uh, and current right now, current is flowing. So in this part here, we've got current, conventional current is moving to the left, right? So conventional current's moving to the left, just like we expect. Electron current is moving to the right, just like we would expect. And what happens is, when we put this electric field here, right, and we've got this thing forward biased on the left side, the base emitter is forward biased, this thing's operating. This base is so thin, it's manufactured so thin, it is super thin. And the emitter is heavily doped. So there's a lot of electrons over here. And the collector is lightly doped. All right. And so we've got this heavily doped emitter and this lightly doped collector. And this is why this thing has asymmetry. You might be saying, well, can't you just flip the collector for the emitter? And you could if it wasn't asymmetrically doped. So heavily doped over here, lightly doped over here. So it needs to be in this orientation. This is how the biases and the voltages and the currents have to be set up. Okay. Now, so we've got the base emitter, we've got this forward bias, we've got current flow, we've got electrons moving across this depletion zone really hot, and they're moving over here, and sure enough, they blow by here. And as they go through here, right, they go through here, and then they get back to this positive terminal, and the current flows. So what do we have? Again, we have a conventional current flowing this way, just like this, going right through here, right? Going right through here. And that current right there adds up with the little base current. So this current right here, all right, and let's give this some names here. Let's do some names here. So I'm going to call this I sub C, and that's this current right here. All right, and then this current going into the base, that's already I sub B, so we got that. And then this current that's flowing out of the emitter here, right? I'm going to call that I sub E. All right, so we've got these three currents. We've got I sub C, we've got I sub E, and we've got I sub B. And these are all conventional currents, and if you flip their direction, then they would be electron currents. But you can see if we talk about electrons in the actual physics, we can kind of see what's going on. So to recap, we have this NPN transistor. It's a three-layer device. The emitter is doped heavily. The base is very, very thin. It's doped with, say, boron, so it's a p-type material. All right, and then the collector is doped lightly. That creates an asymmetrical NPN device, right? We can't flip it around and have the same properties. All right, the transistor acts as a current-controlled switch. What we do is we inject electrons, right? We inject electrons into this region right here, or we push current into the base, and then what happens is we start to get a current flow here. Once we get a large enough forward bias, we pinch down this depletion region between the base and emitter, or this base emitter depletion region, and then we've got a base collector depletion region. We make it small enough so that we get electrons moving to the right. They're recombining with holes so that we have currents in both directions, conventional current, electron current. But because there are so many electrons over here, right, what happens is many of them tunnel right through, and they get right through the space, and they go right through this depletion region over here. As long as we've got this positive, we've got a positive potential over here, dragging them and pulling them and attracting the electrons over to this side. So we get this electron current this way, we get the hole current in the other direction, and then this thing is operating. Now, what's the model that dictates how much current flows and so forth? So there's more complex models, but I'm going to show you something really, really simple that works for most of what we're going to do. So the transistor, the NPN or the PNP junction transistor, can be used in two different modes of operation. All right, one of them is called saturation. All right, and the other one is called the active mode. All right, and then part of saturation, there's cutoff. So when it's totally on and saturated, and then when it's completely cut off and there's no current, that's kind of that mode. And then there's an active mode, and in the active mode, the transistor is acting like a current amplifier, all right? And then there's also a reverse active mode, but we don't really care about that. Okay, so it either works in the saturation cutoff mode. It acts like a switch. If you put enough forward bias on the base, you will turn this thing completely on, and it saturates. That's it. It's just like a switch. It's like a switch. So what does it look like? It looks like something like this. So we've got this base here. Okay, so we're going to call this base. And then we've got this collector here, and we've got this connected to, say, some voltage V sub CC. And then we have this little switch here you could think of, and we'll put a little circle there. And this is the emitter. And then this goes down to, could go down to a load, whatever, goes down to ground. The point is, and then something magical happens in the base here. So if we inject current here, conventional current, I sub B, sufficient enough, we will close this switch. And when we do that, we'll turn this transistor on and it acts like a switch. That's when it's saturated. When it's off, right, then it's open. So it's an open circuit, all right? And so it's got the properties of a switch. Now, in this active mode, it works a little bit different. I don't want to talk too much about this. This is the basis of amplification. And in this case, what happens is that the collector current is a function of the base current, all right? So the collector current is a function of the base current. And so the equation that models that, so let's see here. Let's actually, you guys have got a good look at that, so let's just delete that. All right, so let's draw another transistor here. So we're going to draw this, actually draw it here, and we'll draw our best transistor. And we're going to put a resistor here, and I'm going to put this, I'm going to call this V sub CC. I'm going to call this R sub L. I'm going to call this V sub C. Okay. And I'm going to come down here, and I'm going to put another resistor. I'm going to put this to ground. I'm going to call this R sub E. And I'm going to take another voltage off here. I'm going to call this V sub E. All right, and remember, this is the collector. Let's put another color. And remember, this is the collector. This is the emitter. This is the base. All right. Now on the base here, we're going to have a little resistor here. And right here, I'm going to take this little voltage off here, and I'm going to call this V sub B. I'm going to just call this R sub B. And this voltage doesn't really matter. It's just so that we have a label, but we could call this VS for V source. And we're going to have a current when this thing's on. We're going to have this. As a matter of fact, let's use another color here. All right. So when this thing is operating, we're going to have a current that goes like this. Okay. This current, when it's right here, we're going to call this I sub B. All right. And then we're going to have a current that goes through this part of the circuit here. And here's where things get tricky. So we're going to have this current right here that goes like this. All right. And let's see how I want to draw this. I guess we can. Yeah, we can draw it. We can draw them both going through here. All right. So up here, this current, this is I sub C. And then once we get down into this emitter leg, right, we could label it with one label, but it's the sum of these two currents here. So I sub E, the emitter current coming down here, equals I sub B plus I sub C. All right. Now, and remember, if you look at think about the model we just had up, right, that base current that we get going, that also flows through the entire, body of the transistor from the injection at the base, and it has to exit the emitter. That's why it's called the emitter. And then the current that we cause to flow from the collector also has to flow through the emitter. So the final emitter current is the base current plus the collector current, all right? Now, here is the cool part, all right? And again, this is an NPN transistor right here. Here's the cool part, all right? So let's write down cool part. Okay. The equation, a simple equation that describes these currents is this. So I sub C equals beta times I sub B. All right. So what this says is that there's some constant beta that given some base current, beta times that base current equals the collector current. This is called the gain or the amplification of the transistor. All right. There's also an alpha, but I'm not going to talk about it. All right, if we need it later. This model right here will suffice for most of the things that we're going to do. So for example, let's say, and then what's the beta? Most of these transistors, they're beta, this B, which is beta, or also known as the gain, is on the order of 50 to 300. And most of the time, honestly, it's about 150 to 200, depending on the transistors that you're using. So, okay, so now we know that if we turn this transistor on and we pump some current through it, and we say we pump a milliamp, right, and this transistor turns on, we can use this formula to figure out what the collector current will be, all right? So that's pretty cool. Now, we're going to learn more circuit analysis for this later and how to deal with it. But right now, there's one thing that I can tell you that's going to make it easy to figure out what's going on here so that we can use, Ohm's law and kind of figure stuff out. And that is this. If you look at that base emitter junction, it's a diode, right? And we have to turn it on. To turn this thing on and get it to conduct, we need about 0.6, 0.7 volts. So what that means is this. That means from the base to the emitter right here. So right in here, we could think of, there's a little diode going on here, right? A little diode. I'm going to draw a little diode. And this diode right here, we require, 0.6 to 0.7 volts to turn it on. So when we want to use this transistor and we want to turn the transistor on, first we make the assumption that it's on. And that means that the base emitter junction has at least 0.6 volts on it, and it'll stay around 0.6 volts. Remember the diode experiments, no matter what the current is, it's going to hang around the same thing, and they hang around about 0.6 volts depending on the doping. So once it's on, there should be 0.6 volts. That's how we figure out and do Ohm's law. So if we know what the voltage is at this point, and say it was, I'm just making up a number, say it was 1 volt, then up here it must be 1.6 volts. Same thing if this was, say, 2 volts, then down here it's going to drop, so it'll be 1.3 volts, 1.4 volts. That is how we figure out what's going on inside of the transistor. Okay, so all right, we're almost ready to do some hands-on. And so let's go ahead and let's do one calculation here with Ohm's law and kind of figure things out, and then we'll go to the bench and we'll start building stuff. All right, so let's do that. All right, so hang in there. Okay, so let's go ahead and let's erase all this. Okay, so let's go ahead and we're just going to draw a simple circuit. So let's see here. Let's go ahead and do this. All right, so let's get a transistor here and get a transistor. So we're doing NPN transistors. All right, and let's put some numbers. Let's put 5 volts up here. All right, good enough. And let's put a resistor here. All right, And let's put the emitter. So, and again, let's label these always until you memorize these. Let's put the emitter directly to ground here. Okay, so the emitter is to ground. All right, and this we're going to call this R sub L. Okay, and then I'm going to take this point right here, and we can call this it's V sub C, right? But we could also call it V out. Okay. All right, so far so good. Now we've got this R sub B here, okay? And now let's say we're working with a 5-volt system. So let's put a switch here. Let's put a switch here. Let's put a momentary switch. Here's kind of the symbol for a momentary switch. And we're going to put this up to plus 5 volts. All right, and just a quick little note, remember you can put an arrow if you want and put plus 5 volts. That's one style. Another style is you put a little bar, plus 5 volts. Another style is you can put a little dot, plus 5 volts. Whatever you want, just be consistent. I typically use arrows, but since we have this little arrow on this transistor right now and you haven't seen this before, I don't want to confuse you, so I'm just going to put a little dot, maybe a bigger dot. Okay, so we've got this little circuit right here. All right, so now to get this thing to turn on, the rules are that we need to forward bias this base emitter junction here. We're going to forward bias this by at least 0.6, 0.7 volts and turn that on. All right. Rule number 2 is we need to have and you know what, we can label this also voltage emitter. We also want to have, to turn this thing on, we want to have a current in this base circuit, and once that current flows, that's going to cause a current in the this collector emitter circuit. All right. The thing that models that is that equation that I showed you. So it says that I sub C, or I sub C equals beta times I sub B. Okay. Okay, so we have our equation here, I sub C equals beta times I sub B. All right, now I want to mention a couple things. I think I mentioned them, but let's review just a little bit here. And what that is that the transistor operates in 3 primary modes that we care about. All right, and the first mode is active mode, and the second mode is saturation mode, and the third mode is cutoff mode. All right, and again, we're getting way ahead of ourselves here. We don't have enough tools to understand all these things exactly, but I just want to kind of mention them just so you're kind of aware of it, and then later when we see it again, it'll be more familiar. And then also, just when you're doing transistor circuits, even right now when we go to the bench, this will make it a little bit easier to kind of figure out what's going on. Okay, so when you're in active mode, that's when this equation is valid. All right, so in active mode, the equation I sub C equals beta times I sub B is valid. In saturation mode, basically the transistor is turned into a closed switch, and as much current as can possibly flow through its internal impedance is going to flow. So it's just basically an on switch, right? So this is just a closed switch. And then cut off, it's an open switch, very little current flows, almost no current. All right, just what the leakage currents through the transistors. Now, this is a confusing subject, the active mode, and setting up the transistor in such a way so that you have the proper voltages on the emitter and the collector and the base so that you operate in active mode. The whole idea of active mode is to use the transistor as an amplifier. So, and let me do kind of a black box here. So just imagine, this triangle represents a transistor. We'll call it T. We put in a signal. All right, and we could call this, S0, and then on the output, what we want is something bigger. So we want some gain A times S0 as the output. That's the whole idea of an amplifier. All right, and this is an amplification stage. So a transistor can do this, and there's lots of ways of setting it up to be able to do this. However, what we're going to learn, and I think we're going to cover these later, are some devices called op-amps, operational amplifiers, and they're going to make setting up amplifiers much, much easier so that we don't have to understand how to do biasing, and there's different kinds of amplifier circuits for transistors. They're called classes, Class A, Class B, Class C, and the way that the transistor is set up in the circuit and the bias so that you can kind of amplify a signal. And typically what has to go on is the transistor has to be set into this active region, all right? And once it's set into the active region, then we put a small signal in, and then we get a larger signal out. And setting that up it's not trivial, all right? And we have to learn about what are called characteristic curves of the transistor. And let me show that to you right now. Let me erase a little bit of this. All right, so characteristic curves, and I just Googled and found one here. If you just type in characteristic transistor curves, you can kind of see what this looks like. So this thing is, it's not easy to read and understand even what's going on here, but it's showing the transistor, and over here is the saturation region, and down here is the cutoff region, and in here is the active region. And the way that these things are typically drawn, for a base current, so for a steady state base current of say 20 microamperes, the operation will follow this curve right here. For 40 microamperes, it'll follow this curve right here. So if you set up a base current of 20 or 40 or 60 or 80, right, and these are just generic numbers, then these curves describe the behavior of the transistor when it's in this thing called active region. All right, and so for example, at say 20 microamperes for this particular transistor, whatever it happened to be, then if we move over here to the left, we're going to see that we're going to get this current out of here, right? We're going to get for V sub I sub C, this is current, this vertical graph here, we're going to get about 15 milliamperes. Then the interesting thing is, to see this voltage right here, this is the collector emitter junction voltage. It stays dead the same. So, so no matter what it does, this current stays the same. So this collector voltage can go all the way from, you know, little greater than 0, all the way up to 12 in this particular transistor. No matter what it is, that collector emitter voltage, right, this current stays the same. And again, this current stays the same. So this I sub B and this I sub C stay the same. So all of this is put together to create what's called a load line. And the load line is where we operate the transistor at. And in this point right here, Q, it's called quiescent point. So we bias the transistor where we want to bias it, up at, say, some amount of current for the base current, which then sets up a collector current. So you can imagine it like this. So we've got this amplifier, right? And what we do is we bias it up into a region where we know how it amplifies. We know the amplification is I sub C equals beta times I sub B. So we know some function that there's amplification, and the amplification is linear in this region. So we bias it up there, DC bias it. Then what we do is we take a small signal AC wave, that's our wave that we want to amplify, and we ride it on top of that DC. And as we ride it on top of that, we stay inside of the active region, but we get amplification. So what happens is we, from this Q point, we ride a wave on top of here, and then, you know, we can see the voltage change here, and then you come up here and you can see the voltage over here, the current over here get amplified. And so anyway, the point is that this whole graph here, and we're not going to learn this, and you can learn this on your own if you like to, and how amplifiers work with transistors, but we're not going to use the transistor per se in the active region. It may be in the active region, but we're going to primarily use these as switches, saturated or cut off. All right, but you can use them as amplifiers. They're just not easy to set up, and that's why people invented operational amplifiers, which are basically a black box component that has a bunch of transistors or MOSFETs, field effect transistors inside of it, so that you don't have to worry about all this biasing. You can just put in a current, a voltage, and they have certain behaviors, and you can get an amplifier made very, very easily. And we are going to cover those later. All right, but anyway, this is a characteristic curve, and when you see this, this is kind of what this is about. This is about the active region, the saturated region, the cutoff region of the transistor. Now, let me show you something else. So if we look at this circuit schematic right here, many times also what you'll see, I'm going to draw some stuff we're not going to put in our circuit, but you'll see a resistor here, an emitter resistor, and then what you might see is you might see a pair of resistors like this and going to ground, and this is creates a voltage divider, which we've talked about a little bit. And we'll talk about some more. And this sets that DC bias point. And then we have an emitter resistor right here. And then we do this so that we can pull off different voltages, because VE is always going to be at ground if there's nothing here, right? And then if we want to pass, so this would set up a DC bias point, the Q point. Then what we do is we would put a capacitor here, and then we would be able to pass an AC signal with block DC. And then out here we would get actually you get the inverted. It's going to invert it if you go through it. But anyway, that would be kind of an amplifier, right? But we're not gonna mess with that in this course. Maybe some bonus stuff, but anyway, all right. So we've got active, saturated, and cutoff. So let's look at how we get it into each one of these zones here, right? So for the active region, what we want is we want VB, the voltage on the base, VB. All right, and let's actually mark this here. So what do we have here? We've got VC, VE, and then here we're going to call this VB. All right, the voltage on the base here. All right, so we've got VB has to be greater than V sub E, and V sub B has to be greater than V sub C. All right. Nope. Sorry. So V sub B has to be greater than V sub E, but V sub, and this is always confusing, has to be less than V sub C. Or we could write it like this. We could say, here's V sub C, and then V sub C is greater than V sub B, and V sub B is greater than V sub E. All right, so this is when it's active. So in a nutshell, the base voltage is going to be between the collector and the emitter, and the collector is greater than the emitter. All right, and I think I have, let's see, yeah. So here's the Wikipedia page for bipolar transistor, and this is a really good reading right here. You could do worse things and read this. So if we look here for NPN, and let's see here, NPN, and we want to forward active. So the base voltage is greater than the emitter, and the collector is greater than the base, which is what we have here. So the collector is greater than the base is greater than the emitter. Okay, saturation is this case. The base is greater than the collector, and the base is greater than the emitter voltage. All right, and again, we can check that. And again, I don't believe Wikipedia, right? Please look at a book that's peer-reviewed and all that. I mean, I'll take this with a grain of salt. Take Wikipedia with a grain of salt. It's peer-reviewed, somewhat. People go on and edit it and whatnot, but read a textbook if you want to make absolutely sure. And sometimes you'll copy something and someone's copied something that someone else copied and it's wrong, and you want to be careful. But in any way, in any event, saturation, base is greater than the collector, and the base is greater than the emitter. Okay, so, and that's what I think also, so I think we're okay there. All right. And in cutoff, it's just an open switch. All right, so there's no current flowing in the base whatsoever. So in this case, we can just say I sub B is equal to 0. All right, so the thing is completely cut off. And also, to have this happen, the base voltage would be less than the emitter and less than the collector, right? So if you wanted to put that, you could say the base voltage is less than the collector and the base voltage is less than the emitter. All right, and that's going to make the transistor be off. Okay, so getting this set up is a little bit difficult in the active region to get it set up in the active region and bias it up right, and we're not going to mess with that. But we are gonna keep this rule in mind here, all right? And if we build a simple circuit, we can take advantage of this until we push it into the saturated region. So what we can do is we can build a simple circuit, and if V sub B is greater than V sub E, and if V sub B is less than V sub C, and we set up an I sub B, then we know that I sub C will equal beta times I sub B, and we'll be in the active region. If we keep pushing that base current higher and higher and higher, then we'll push into the saturated region. So what's really happening is, back to our little graph here, we were in one of these curves, and we kept going up, 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 up the curve, and as we keep going up, up, up the curve, and then this VCE, this voltage, we kept making this smaller and smaller and smaller, and we kept going this way, this way, this way until we ended up over in the saturated region here. So, anyway, that's what we do when we turn this thing into a switch. We just turn it full on, and then the transistor just turns into a switch. But if you're inactive, then you can use this equation to figure out what the current should be. So we're going to do some stuff with that. Okay, so I think I've thoroughly confused you, hopefully. But just step back for a second, and the whole point of this is it's two diodes, the two diodes back to back. The transistor is used as a amplifier or a switch. We're going to use it as a switch primarily, and the circuit that we're going to kind of use to set things up is we'll just have a base resistor here to set up a current. We'll make sure that we forward bias the base emitter junction, and you remember again, what's here is there's a diode here, right? And plus to minus, and we want to get that thing around 0.6 to 0.7 volts to forward bias that base emitter junction. And once we do that, this thing will turn on, and then we can either be an active, saturated, or cut off. There's one more mode also called reverse active, which is when you're using the transistor in the wrong direction, which we don't care about. Okay, so that's enough of that. So let's just use this transistor in some experiments. Let's look at them, let's play with them, and let's get some hands-on so we can kind of get a feel for this stuff and see what we can do with this, all right? So let's go over to the bench cameras and let's go have some fun, all right? I'll meet you there. Okay, all right, so here's the fun part, which is what I like when we actually get to do something. All right, so first, what I've got here is some of the components that we're going to play with. And again, we're going to do this fast and furious as usual, and we're just going to kind of make stuff up and build some circuits as we go. We're going to be using the model on the computer in the drawing program, kind of is what we're going to do with the transistor for a switch, a saturated switch. And then all you really need from your parts are, if you want to follow along, is you need your NPN transistor, or you could use a PNP if you want to reverse everything, a couple NPN transistors, your resistors, right? I've got 100 here, 220, 330, I've got 10K, 2.2K, 3.3K, a bunch of different values, in even 10 ohm. Got my hookup wire, and then over here I've got some of our diodes from our diode experiments, so we can mess with those. I've got my solderless breadboard with my power hooked up to it, and again, you could have any kind of power you want. We're going to be using 5 volts for these experiments though. So again, having a bench power supply would be really useful. If not, then you're just going to have to use a DC supply, a regulated DC supply or something, but it's something you just got to kind of have to be able to make adjustments. All right, and then a couple little momentary switches here. Okay, so the first thing that I want to do is let's take a look at some of these transistors real quick. And so here is a little strip of transistors. Let's zoom in so you can kind of see this. And then we'll go to the zoomed camera. So that's how they come, and again for through hole. And these guys right here are these are 2222s, so these are 2N2222As. These are one of my favorite little old school transistor. There's also the 3906 and the 3904. This is an NPN transistor, all right, and you can Google and look at the data sheet. And so if we take a close look at this under the zoomed camera here, and let me get it to cooperate here and get the angle right. Okay, you can see it says PN222A, all right, and this one is not labeled at all, so there's no emitter base collector. Now, One of the problems you're going to find when you're playing with parts is if they're not labeled, you don't know what you're dealing with. And the problem with that is you might make an assumption and you might be wrong. So for example, typically, and these things are this half moon shape, right? Typically, it's emitter, base, collector. So from the flat side, emitter, base, collector, but I've seen it be the opposite, collector, base, emitter. So you have to test it, or you have to know the part, or you could potentially burn it out. All right, and then here's another one. All right, 2N3906. See that little M on the bottom left? That's a Motorola. This is a PNP. All right, and then here's another 2222A. This is a Fairchild part, another NPN. And then what's this one? Here's a 3906, and then this is, I don't know, SNN Siliconics. And this might mean emitter base collector, but you never know. All right, and then there's another one, and let's see, is this one the same also? And here's another. This is another PNP. All right, so I'm showing you all these because I want to show you that they do not test the same. All right, so let's go back over to the larger camera view here. All right, and now you can test transistors as if they were two diodes, and you could do some math and compute if they work and all that. But rather than do all that, let's just use a tester. So I actually have a transistor tester. So in many meters, there will be a transistor test. So see this right here, EBC. And then it's got PNP and NPN, and then H sub FE, which I think I mentioned. If I didn't, I'm going to mention it right now. This means the gain. This is that beta. So H sub FE. Now there's actually two H sub FEs. If it's uppercase, that means the DC gain. And then there's H sub little fe, and that means the AC gain. All right, but for now we'll just call it H sub fe or beta, and it just means the gain. All right, so first we're going to put this meter into transistor mode. We'll put it into NPN mode. All right, and let me actually zoom out just a little bit so you can see that. Okay, there we go. All right, and then we're going to get one of our transistors. Now what I want to do is I'm going to actually get two transistors from the exact same family. So we could get them off this, but let's see if, I think I've already got a couple here that are from the exact same family. All right, there's one. There's one. Okay. So you got some transistors, you want to see if they work. Okay, these are both Fairchild 2N2222As, okay? The gain is typically 150 to 300. Remember we said that the beta, so let's see. So we're going to put it in, and you see it says emitter, base, collector, and then base, collector, emitter, and so forth. So we're just going to put it in assuming this is emitter, base, and collector, which I think it is. Be careful. Pop it in, and sure enough, it's working. The gain is 200. Let's flip it around. Okay, and it doesn't work. All right, so that's the correct orientation for an NPN. Now, if we put it in PNP, what happens? Does it explode? No, it just doesn't work. All right, and that's what it should do. So we get 195, 196 as it stabilizes for one of our transistors. We get the same exact manufacturer, same exact part from the same exact little, I ripped them off one of these, right? Are they the same? Now look at that. So again, take it out, put it back in. 199, so a little bit different. So we're seeing about a 2% deviation there, right? Now, that's why, so what this means is, when you use a transistor as an amplifier, this is a concern, right? The gain is different for every transistor potentially. So how on earth could you make a right channel and a left channel have the same gain? When you build an amplifier, we use what's called negative feedback, and we design the circuit such that the actual gain is irrelevant. So as long as say like the transistor has an actual gain of 200, we never use it more than say 10 or 20 or 30 times. And we use a feedback circuit, so the gain, when you do the math, right, the gain actually falls out of the math, so the circuit amplifies irregardless of what the actual gain is, as long as you don't exceed the gain. That way, as long as both transistors could do, say, a gain of 30, which they can, 196 and 195, whatever, it'll still work. All right, and that's when you start talking about amplifiers and feedback loops and so forth, and the math gets a little bit complicated, but anyway. All right, so we got two transistors here. They look good. Let's get another piece of equipment. So remember, we're paranoid. We don't believe anything. So here's another meter that has the same functionality. See it in the bottom left there. All right, so I got another meter with the same thing here. And let's put it on NPN mode. And can you see all that? You can barely see it. Yep, right there. Good, good, good. Okay. So I'm going to put my transistor in here again, EBC, and get it in there. And I can feel it's not making contact. All right, I'm going to have to hold it. All right, so 199, yep, about the same as what the other meter read. And there we go there. And again, these contacts are a little bit old. 200. You can see, I don't know if you can see this capacitor. This is for me burning something up. I don't know, discharge capacitor or something. So this meter's been through a lot, but it's a good meter. All right, again, push it in there, 200. So both meters are reading about 200. We're going to call it about 200 to make the math easy. So 200 on both meters for the gain. So if we use these transistors in active mode, we should get a current gain of about 200, all right? So that's the first thing to note. All right, so we're going to take our two transistors, we're going to put them here. We're going to put all these other ones over here, away. And let's start building a circuit here. Let's just start. All right, so we're going to build our circuit, and let me get this in here so I can work. All right. Okay, and I'm going to bring this down just a little bit so you can follow along a little bit better, but you know what all the parts are here. Okay, so let's put our transistor in the circuit someplace. Put it right about here and see it fits in there nicely. All right, so remember, it's emitter, base, collector. Emitter, base, collector, right? All right, so let's start off and let's put the emitter to ground. All right, so we're going to put the emitter to ground. So we'll do that. We'll put the emitter to ground. And actually, that's not long enough. Let's get a longer one. Not too long. Okay, so we'll put the emitter to ground. Great. All right, the collector we're going to put up to the positive rail, and let's do that through a, let's do that through a 1K resistor. Let's find a 1K resistor over here. Here we go. So what's 1K? Brown, black, red. Brown, black, red. All right, so here's the collector right here, and that's up to the +5 rail. Okay, and now let's put a base resistor. So, all right, so here's the thing. If we assume that this is in the active mode, right, or well, if we assume that we're going to set it up in the active mode, if we set up a base current, we should get whatever the collector current is through the collector circuit. But since we have this resistor here, this is going to control the maximum amount of current and the voltages and all that occur inside of the collector emitter circuit. So that's why setting up and running things in active mode is a little bit more difficult, because you actually have to design the circuit a little bit better, right? So we're going to use the model of the active mode just to kind of get a general worst case scenario of what's going to happen with the current, but we're going to just assume that this thing is going to end up probably in saturated mode like a switch, and we're going to check the voltages. But again, we kind of work both ends at the same time to make sure that we're setting this thing up. Okay, so we got the 1K in the collector circuit here, all right? And then in the base circuit, let's go ahead and let's start off with a 3.3K for bias. So we're going to bias with 3.3K, so that's orange, orange, red, all right? So I'm just going to put this in here to the base, and all right, so we've got that, and now I'm going to take that and I'm going to put a, ow, I just impaled myself right there, just did it. All right, I'm going to now put a switch here, okay, and I'm going to now put this to the top rail, like this, all right. Okay, now my power supply is on. There's 5 volts right now. So let's just check the voltage so you will believe me that we've got 5 volts. We always want to check things. Okay, so can you see that? And can you see that? Let's back out. All right, so we can see both things here. Let's get our probes. We're in voltage mode. Okay, so the top rail and the bottom rail should be 5 volts. So if I go up here and I go here, all right, that's 5 volts. Okay, and so right now, when the circuit is completely off, let's take a look at what some of these things are. So if you want to look back at the screen, so the emitter is connected directly to ground. So that's going to be at 0 volts, so we know that. So if we check the emitter, right, and there's the emitter right there. Remember, it's emitter-based collector, very carefully. It's at ground, right, 000 millivolts. That's expected because there's a wire right there. Now, what's the base at? Let's find out. The base is at like a nothingness voltage, right? It's fluctuating all over the place, and it shows a negative and all that. What's really going on is that, remember, this is a semiconductor device, right? And that base, there's a voltage across the collector to the emitter right now, and there's no voltage on the base, right? It's just floating because we have the switch connected to it with this resistor. It's just floating. And what's occurring right there is there's minute charge inside of the base from the collector to the emitter, and momentarily there's noise, and we're actually picking that up on this meter here. And you can see the meter right now is floating all over the place also, just from the air. So, but when we put it here to these actual contacts, it floats back and forth, right? Because there's actual little minute amounts of charge, and the meter itself is a load, all right? So anyway, bottom line is there's nothing happening on the base. Okay, now let's go check what the collector voltage is, and the collector voltage is right here. Now, here's a question. There's no current, there shouldn't be any current in the collector emitter circuit right now, right? Because there's no base current. So if there's no current, there's no voltage drop over this resistor. If there's no voltage drop over the resistor, what voltage do we have up here? We have 5 volts. What voltage do we have right here? We should still have 5 volts because there's no voltage drop, right? Because remember, V equals I times R. If I is 0, then there's no voltage drop. So we should read 5 volts right here. Let's see if we do. And sure enough, we read the exact same voltage as the top rail, 5 volts. Okay, the transistor is completely off. The transistor is in cutoff right now, right? Okay, so now let's go ahead and we're going to turn the transistor on. And as we turn the transistor on, we're going to check these different things, all right? Now, probably let's pull the switch out and let's just force it on, because I'm going to want to make some measurements here, and it'll be a little bit easier. And then we'll put the switch back when we do a couple other experiments. Let's just force this thing on. Okay. So now we forced it on. So there's a voltage on this side of the resistor. So now let's see, what is the voltage drop over the resistor? So the voltage drop over the resistor is 4.3 volts. Okay, let's compute the current flowing through the resistor. 4.3 volts, so V equals I times R, right? So 4.3 divided by, that is a 3.3K, 3.3 x 3. So we've got 1.3 milliamps, 1.3 milliamps. So we've got 1.3 milliamps getting injected into that base. If this was in the active mode, right, then we would have that times about 200, because that's the beta gain, and we would end up with 260 milliamps flowing through the collector emitter circuit. But we can't. Why? Because what's the best we can do? Well, we've got a 1K in the collector emitter circuit there. So if we take 5 volts divided by 1x3, the best we're going to do is get only 5 milliamps, right? Because the way we've set this up. But the question is, did we put this into, say, saturation, right? Is this thing saturated? So let's start measuring some things. Okay, so let's measure what the base is. So the base voltage, the base is right here. So the base to ground is 0.7 volts. So that means that the base emitter junction is forward biased. So this transistor is on, so it's forward biased. Okay, so that's good. We forward biased it, so we know that that's going. Now, the voltage on the emitter is 0, right? The emitter is connected directly to ground. So the base voltage is greater than the emitter voltage. That's one of the constraints for being in the saturated mode. 0.7 volts is definitely greater than 0.0 volts. Okay. The other consideration is that the base voltage has to be greater than the collector voltage, right? So let's check it. So where's the collector? The collector's right there, and we check that. All right, and the collector is reading at practically 0, 24.6 millivolts. So 0.7 is definitely greater than 26.4 millivolts. So if we look back on the screen, right, and let's take a quick look at that. So back here on our screen, on our drawing program, where are we? Saturated mode. V sub B is greater than V sub C, and V sub B is greater than V sub E. Good. All right, so we must be saturated. So we're in the saturated part of that curve. All right, so the transistor is fully on. Okay, so back here on the bench, the transistor is totally on. at best, we could have got 240 milliamps, but we can't because we've got this resistor in the collector emitter circuit here, all right? But this thing is still acting as a switch, all right? Let's measure what the current is, even though we can measure the current, the voltage over the resistor there, right, to compute the current. So again, let's do that. So what's the voltage over this? And it should be almost 5 volts, and it is. It's 4.9. There you go. Let's get that in the screen there. And it's 4.98. And of course it is because we just measured the collector emitter junction resistance, and it was millivolts, 24 millivolts. So this thing is basically 5 volts. So 5 volts divided by 1K is 5 milliamps. So if we take a meter and we open the circuit up right here, we better get 5 milliamps. Okay, so let's go ahead and do that. Again, I know it's obvious to most people, but I don't trust it. So let's make sure. All right, the laws of physics sooner or later will bend, and things will not do what they're supposed to do. It happens all the time. All right, so I'm going to get another meter here. I'm going to put it in amp mode. And looking at this meter, where are we here? So we'll put it on 200 milliamps. All right, so I got another meter here. Okay, and we're going to plug this thing in. Here we go. And we better get 5. Okay, so we've got 6.3 milliamps, right? What is going on? So what is going on here? So wait a minute, remember what we said. We said that the emitter current is the base current plus the collector current. So the collector current going into the collector is 5 milliamps. But what is the current going into the base, right? It has to go someplace. What's the current going into the base? Let's measure that, all right? And here, this is why this is cool. All right, so let's go with our other meter. Let me see, can I put it right here? So you can see this all at once. Let me see. Okay, so again, going into our base is 4.28 volts, 4.28 volts. All right, so let's do the math. So 4.28 divided by 3.3 x3, right? V equals I times R, right? And that's 1.3, look at that, 1.3 milliamps plus the 5 milliamps is the 6.3 milliamps. So remember, the emitter current will always be the base current plus the collector current. Typically though, when you're using the transistors, the base current is going to be so small compared to the collector current, right? It's, you know, you don't even notice it, so that the collector current coming in to the top would exit coming out of the emitter, and you would have, if you just ignored even the base current, it wouldn't make your calculation off by but 1% or so. But in this case, it's a big chunk. It's 1.3 milliamps of the 6.3 milliamps, so you have to consider it. So the transistor is doing exactly what it should do. It's actually running in saturated mode, all right? And now let's put our switch back. Let's put our switch back. And I'm gonna keep this meter over here hooked up, but I'm gonna put our switch back. Okay, so we're gonna put our switch connecting the power. All right, so I can show you this. So we're putting our switch back up here. Okay, all right, and let's put our amp meter here so we can see it. All right, so now there's no current because it's off. There's no base current, so there's no collector current. Now I turn it on and I get my 6.3. Okay, so now we basically got a digital switch with 6.3 milliamps. Let's get a little bit more current. So we've got this 1K resistor up here. All right, why don't we increase this current by decreasing that resistor? So let's not get too greedy, but let's go to, say, I had a 330 here someplace. Here's one, I think. Orange, orange, brown. So here's 330. So this will give us 3 times the current, roughly, right? So we'll put that up there as the collector limiting resistor. All right, so now we got no current. So now we're expecting about 3 times the current. So we should get basically 5 volts divided by 330 here, plus our base current. And I turn it on, and look at that, we got 16 milliamps. Okay, so 16 milliamps, that's pretty good. Now let's use that and let's put something inside of this circuit. All right, so now what we're going to do is, and there's a couple places that we can do this at. We can put something inside the circuit here, or we could put something at the collector junction. All right, so if we look at the collector junction, let's look at the collector junction. And then this is, different ways of using transistors. We can do different things with them. So let's look at the collector junction. Let's get our meter here. And all right, let me put that one there so you can see our ammeter there, and there's our voltmeter there. All right. And again, I'm trying to keep things close so you can really see them because this stuff is small. All right, so I'm going to go right there in the collector junction, and then I'm going to go, let's see here, bear with me, bear with me, bear with me. And then I'm going to go to ground here. Okay, and I'm going to put this up. Let me see, let me see. Okay, I'm not happy with that. So again, in electronics, don't fight yourself. Just do things, make it easy if you have to. All right, so what we're going to do is we are just going to add another probe. Okay, so we just added another little connector so we can measure voltage properly from here. Okay, now, so we've got our ammeter at the bottom, we've got our voltmeter up here, and so now let's take a look. Okay, when the circuit is off, when the button is off, we've got no current flowing, so we should see 5 volts at the collector junction because there's no current flowing in the collector circuit, so there's no voltage dropping over this resistor, right? So now we press the button, and sure enough, what do we get? We have 16 milliamps flowing through the circuit, and now the voltage is practically zero, right? It's 89 millivolts, so we've got 16 milliamps there. All right, so this is working as a switch as we would expect. All right, so now let's go ahead and let's do something with this. So now we've got a circuit basically that we can turn on and turn off in saturated mode with a decent amount of current, 16 milliamps, right, which is being limited by this resistor up here up in the collector to a power rail. All right, so there's 2 ways that we can add something to the circuit. We could put something in the emitter to ground circuit, all right in that current path. We could do that. We could also put it at the collector junction to ground. All right, so let's start with that and let's see what that looks like. So I'm just going to move these meters a little bit here so you can kind of see what's going on. And I'm going to zoom in just a second. There we go. All right, so let's go ahead and let's put an LED to ground. So what we're going to do is, here's the output of the collector. All right, so I'm going to just take that. And I'm going to bring it to the other side of the solderless breadboard. And this stuff gets messy. It's okay. But when you make it, if you want to make something that you're going to use or as a prototype, make it much cleaner, obviously. But we're just hacking around. All right, so I'm going to hook this up to a light emitting diode. So I'm going to hook it up to the anode and then the cathode. The long side is going to go to ground. All right, now, so first you notice it's on. All right, and we're going to talk about that in a second. Now, normally we might want to put a current limiting resistor here, but we've already got one. No matter what, current is flowing from the top rail through this resistor and then to this LED, all right? The transistor right now is acting like a switch, and this switch right now is completely off. Because it's off, there's no current flowing through the transistor. In fact, if I were to pull it out, nothing would change. So let me show you this real quick. All right, so right now we're showing 2 volts at the collector junction, and we're showing no current going through the transistor. The transistor is completely off, which it should be. This button is not on. There's no base current, right? But instead of 5 volts, now there's 2 volts. Why? Well, we put a load on here. We put this load, this LED, so now current is actually flowing through the resistor, but not through the transistor, and then through the LED, so there's a voltage dropping over the resistor and over the LED. What's the LED's typical voltage drop? Right, the LED's typical voltage drop is about 2 volts, and lo and behold, it's about 2 volts, so the rest must be dropping over the resistor. But just to prove to you that nothing, this transistor is doing absolutely nothing, I'm going to pull it out. Ready? Nothing happened. It's not doing anything. That's why. It's off. All right, let's make sure we put that back in there. Okay. Now, the question is, what happens when I press this button? When I press this button, we're going to inject current into the base. We're going to turn the transistor on. We've kind of ascertained we're saturating the transistor, putting it into the saturated portion of the characteristic curves. It's going to turn on. When it turns on, we're going to get current flowing through it, all right? And it's going to act as another current sink, all right? And then what's going to happen is it's going to pull current away from this LED, all right? And the LED is going to turn off. So the LED turns off now. So what's happening now is we have our full 16 milliamps are actually flowing through the transistor. Look at the voltage on the collector. Look at that. It's 89, call it 90 millivolts. It's basically zero. There's 0 volts over this LED now because it's right at the collector. So what happened is the transistor turned on. It's dragged the collector all the way down to ground practically. It's practically down at ground. So the collector emitter junction right now is almost 0 volts, right? It's 89 volts, millivolts, excuse me, 89 millivolts practically down to ground. So basically, when the transistor's off, this output at this collector is on, and when the transistor is on, it's off. So this is why this is called a common emitter configuration. It inverts the signal. It tends to invert the signal because when the transistor is off, you just basically have this top, what we call R sub L resistor, feeding whatever part of your circuit is the output. Then when we turn the circuit on, that R sub L is still feeding it, but the transistor is going to ground and sinking all the current now, and there's our current. All right, so that's one configuration. Can we use the other configuration? So let's pull the LED out. Notice how it goes back up to 5 volts because there's no load on it. And let's put it inside of the emitter leg to ground. So we're going to put it in the emitter leg to ground. So we're going to go right here, we're going to do that. Now, word of caution. We've got this current limiter here, right, which is going to limit the current to 5 volts divided by whatever this resistor is, which now is 220. So we know we're safe on that. We know that we're possibly pulling about 16 milliamps through here, so that's okay. And then what we would be concerned about is now, since we're going in this emitter leg, we're already measuring the current in the emitter leg, so whatever the base current also would get added to that collector current to create the final emitter current, we should be okay because we're measuring it right here. But if we were to measure the current up in the top, in the collector part, it would be a little bit less because we're not getting that base current added to it. So remember, we get the collector current coming down and we get the base current, and they both add up to make the emitter current. But it was at 16 roughly, so we're okay. So I'm just going to pull this wire here, and I'm just going to move it a little bit to the left here. Then I'm going to put our light emitting diode. You know what? And let's do a red one, because this will turn on a little bit lower forward voltage just for kicks because we've been using green. All right, and again, we're going to put the diode in the correct orientation. So we want anode on the left because current's going to come down and flow this way to ground. So we want the anode on the left, so that's what I'm going to do. All right, and you know what? I'm going to turn the power supply off because I want to surprise you. So we're going to put this in right here. All right. Okay, so the power is off, the LED is off. I'm going to turn the power on. Should the LED turn on? Yes or no? And it didn't. And of course not, because there's no current flowing. Why is there no current flowing? Because there's no base current flowing. If there's no base current flowing, then there's no collector emitter current flowing. Now, what's the voltage on the collector? It's 5 volts as it should be. The transistor is off. Let's turn the transistor on, and then we're going to dump 16 milliamps down through this diode. Ready? And do we do something wrong here? Okay. All right, so what just happened here is this. This LED, all right, has the flat spot on the cathode, except in this particular LED, the cathode is the small post instead of the big post. And so I just looked at it visually and thought it was the other way around. So the anode is on the left, the cathode is on the right, the anode is the big guy, and the cathode is the little guy in this particular case. So that's what happened there. All right, and again, that's why you got to test these things. Sometimes they just make them a different way. Everyone wants to do things their way. Okay, transistor is off. We've got no current flowing in the emitter, right? Got no current flowing in the collector emitter circuit at all. We've got 5 volts at the collector, right? There's no load on it, so nothing's going to happen. We're going to turn this thing on, and we should get our current through the emitter, and this LED should turn on, and it does. And what's our current now? It's 10 milliamps instead of 16.7. Why? Anyone? The reason, of course, obviously, is that this diode has some forward resistance, right? It has some impedance, and because of that, we're going to get less current in the overall circuit, right? Because we just added a resistor, in essence, to it. Turn it off. There we go. All right. Now, let's do one more thing for fun. Let's go ahead and re-add our collector LED back to the circuit. And now on this one, the cathode is the flat one. All right. So we're going to put it here. And now look at this. That one is on, right? This one is off because the transistor is currently off. Now let's turn the transistor on and let's see what happens. How cool is that? All right. So it's doing exactly what it should do. So we just used the transistor as a switch. We showed how we can get either a positive or negative kind of output. We can get an inverted output if we go from the collector, or we can get a positive output, or the same, if something is high, it'll remain to be high. If current's on, current will be on. If current's off, current will be off, if we put it into the emitter circuit. All right, so there you go. Okay, so very cool. So now that we've got this thing as a saturated switch, let's use a transistor for something we might use it. And again, we're getting ahead of ourselves, but who cares? This is fun. Let's have some fun. We've been doing a lot of theory, and let's just build stuff. Okay, so one of the things that you'll see people do a lot is, and let's turn the power off. They'll use transistors to drive larger loads, like a motor or something like that, right? And now, later I'll teach you that I don't want you to do that. I want you to do it with a MOSFET, because it's a much better switch than a transistor. But for now, we can do that. All right, so this transistor can safely conduct about 200 milliamps before it just gets too hot. So if we have a load that's under 200 milliamps that we want to control, we can put this thing into saturated mode and we can control it. All right, so first let's go and let's think what our circuit is going to be. So let's just undo some of this stuff. We got kind of a mess going on here, right? Let's just kind of do a reset so we can see what it is we're doing. Let's zoom back in here. Okay, so let's take some of this out. Remember, clean, clean, clean. Straighten our wires out. Straighten our wires out. Let's put our LEDs back. Let's put these little guys, straighten them back out. All right, very important to keep things clean. Everything will just become a mess otherwise. All right. And I've impaled my finger once today, and I keep doing the same finger. You can't see this, but this finger gets impaled all the time, all the time. All right. Okay, so we've got our circuit here, and we've got our 220 up here. So first thing is, let's leave that 220. We've got this 3.3K here in the base, okay? And the first thing I want to do is, instead of the 3.3K, let's get a smaller, let's do a 1K. So when we turn this resistor on, I really want to drive a lot of current into it. I want to make sure I saturate it really hard and I turn it completely on. Okay, now down here in our emitter to ground leg, right? Let's go ahead in this new configuration right here. In fact, instead of 220 right here, let's make that a 100 ohm. All right, 100 ohm. And let's make it this big 100 ohm brown, black, brown, right? This is probably a half watt resistor instead of a quarter watt, because we're going to put some current through here. All right, so let's put this right here. Okay. All right, so we've got 1K to the base. We've got 100 to the collector. All right, and this is limiting. Now, if we go to our calculator, what's the most current we can get through this circuit? And we may have to change this. So V equals I times R. V equals I times R. So what's current? That would be V divided by R. So V is 5 volts divided by R, which is 100 ohms. And that's only 50 milliamps. And I'm going to tell you we're going to need more. We're going to need more. So instead of the 50, you know what? But let's leave that in there for now for an experiment. So we know that the best we're going to get out of here is 50 milliamps, because that's limited by that. Now, in the collector circuit, we could go right off here to drive our load, but we're going to put this in the emitter circuit. All right. The first thing I want to do is I want to show you this motor. So here's a motor. This is actually a pump. So this is a motor connected to a plastic pump, and there are many, many kinds of motors. And we're not doing mechatronics in this course, but this is something fun, so we'll just do it. And we've got this motor here, and connected to a little pump that pumps air actually. And this is a really, really expensive motor. This is by a company called Smart Pumps Inc. in San Jose, California. That's actually where I was born. And these little pumps, this one happens to be the AP-2P01, and they make 3 or 4 of these micro pumps. They're awesome, but they're like $60 to $80 each, if you can believe that. So only big OEM manufacturers will buy these to put into products, and you can get them at lower prices. But if you Google and go onto eBay, you can find these for $2 to $5, and these are really, really, really good if you want to pump air. All right. So what I want to show you is, if you look closely at this, and let's go to the zoomed in camera on this one. So if you look closely at this, let me get it to focus. It says 3 volts DC at 460 milliamps, all right? And that's 300 millimeters of mercury. That's the pressure that it can pump at. So this thing requires 460 milliamps at 3 volts, right? That's a lot. Well, at 6 volts, it would take probably half the current, so 230, but 6 volts would be probably overpowering the motor and maybe damage it. But in reality, you can kind of get away with that with these small motors. It'll be fine if we run it at 5 volts, and we'll be able to put much less current, and it wouldn't be pressuring at 300 millimeters of mercury. And you can look up millimeters of mercury as one as a measurement of pressure. But we don't really need all that. We just need a little bit to turn the motor on and maybe pump some air. Okay, so we're going to turn the 5-volt supply on, and I'm just going to directly connect this thing up and hot wire it so you can see it. So here's the motor. All right, I'm just going to hold it here, and I'm just going to hook it directly up to the 5-volt rail. All right, ready? Here we go. How cool is that? All right, and if I look at the power supply, actually, let me show you. So I'm going to put the monitor, the camera on the power supply, and you can see, so the camera's on the power supply. You can see it's pulling 330 milliamps, or a third of an amp, which is exactly what it should do. All right, so let's turn that off. So we want to turn this thing on with our transistor circuit. Can we do it? So let's give it a try. So now we're going to take the, and here's another thing. Let me show you this. This motor is not polarized, so it'll go that way. It'll go that way. You notice, though, I've actually polarized the connectors here because it's only going to pump air in the proper direction if you power it with red to plus, okay? So in our circuit, we know that current is going to flow from the collector down through the emitter down to ground. So that's the direction of conventional current flow, so that's where we want to put the plus. So here's the emitter. We're going to take the emitter directly to ground. All right, so we're good to go. We've got that. All right, and now the question is, when we turn this thing on, will we get enough current to turn this thing on? Okay, let's put a current meter in here too, so we can measure what the current is. All right, so let me grab the current meter, and of course all the cables are getting all tangled up, and that's what they do. All right, so we've got the current meter. We've got our little connector. Oh, I hit the camera, sorry. All right, so now let's go like this, and let's get the output here from our emitter, and we're going to take that output and we're going to put it right here. Okay, and then we're going to take our little current shunt. We're going to go like that, and then we are going to, so that's now in the circuit. So now when we hook our motor into the circuit as well, we'll be able to measure the current and turn the motor on, maybe. All right, so now let's back out here a little bit so we can see what's going on. All right, so we got our motor. I'm going to put the motor right here so you can see it, so there's no tricks. All right, and so the question is, we got this on 200 milliamps, and we know we can't flow more than 50, so 200 milliamp scale should be fine. And let's go ahead and press the button. Let's see what happens. Ready? Nothing. But we are getting the 50 milliamps. It's just not enough to turn this motor over. So the motor is stalled right now. This is called stalled. Just not enough current to get it going. All right, well, let's get rid of this resistor and let's bring the resistor down. So let's bring it way down. Do we have a 10 ohm? I do. Here's a 10 ohm resistor, and so I'm going to put the 10 ohm in there. Let's do the math. Let's get your calculator. Unless you can do it in your head. Can you do it in your head? So what's the maximum current through the 10 ohm resistor with a 5 volt source? So V equals I times R. I equals V divided by R, right? So what's that? So that's 5 divided by 10 equals 0.5 or half an amp. In other words, we're going to allow up to half an amp. So whatever the transistor saturates at and allows for current flow, up to a half amp will flow. So this is definitely not going to limit the transistor, because we know this transistor probably can only flow 200 or 300 milliamps at best. So this should do it. All right, so here we go. Ready? 1, 2, 3. Okay. All right, now I think, no, we're okay. And again, okay, so what's happening now? So what's happening now, this 200 milliamp scale, it's saying 0L. We need to put it on a higher scale and put it on the 10 amp scale. Now it's to 10 amp. All right, now, again, we go 270, there it goes. 200 milliamps and it's going. Now, we have it inside of the emitter circuit here. And that's okay, but what's happening is as this motor is turning around and turning over, it's modulating the voltage on the emitter, right? And so remember, the emitter needs to stay forward biased, right? And because of the back EMF caused by a motor and the inductance in it, it's kind of not a good thing to put this in the emitter leg. So instead, let's do this. Let's put the motor up in the collector leg. So we're going to put this back down to ground. We're going to put the emitter back down to ground, so we've got a nice ground on the emitter, right? We like that nice ground on the emitter. And in fact, we'll still put the meter in that circuit, go into ground, so we can measure what the final current is down through the emitter. All right, we're going to do that. Okay. Okay, so we got that in there. Okay. But now what we're going to do is, instead of the resistor, we are just going to completely open the circuit up and we're going to put the motor in here. All right, so we're going to put the motor from plus to the collector. All right, so now we got our meter here. We've got everything good to go. So now when we turn this thing on, whatever we turn that transistor on to, fully saturate, it's going to turn on, let current flow, and the load will be the motor, and the motor will dictate the maximum amount of current that can flow. So let's see what happens, and the transistor is just going to act as a switch. All right, so here we go. There we go. Hear how loud it is now? And now look at our current. We've got almost 0.3, the same as a dead short when we were connecting it directly to the power supply. That's what we want. Now, if I were to put my finger on this transistor and hold it here, it is a teeny tiny bit warm, all right? But not bad. Okay, now, one thing that you'll learn is when you want to power inductive loads is that every time this motor turns around, what happens is that the field collapses and then a back EMF is pushed through this transistor. So what you do is you put a diode across this, okay, and it's called a kickback diode, and that kickback diode protects the transistor from these voltage spikes that get thrown back. So let me show you real quick, because this is an important little tidbit. So let's take a look on the computer real quick at the kickback diode, and then we'll come back, all right? So we have our circuit here, and then basically what we did was we took the motor, right? We took the motor, and we put the motor right here where our R sub L was, okay? And we're talking just about this little kickback diode situation. So here's the motor, and we're going to represent the motor as a coil of wire and like a circle, all right? And we can say motor. All right, and then what we're going to do is to protect the rest of the circuit here. So this thing's going to turn this motor with this large amount of current. So what we do is this. Normally current is going to flow downward through this inductor, which is the motor, right? It's an inductive load. So what we do is we put a diode backwards on it like this. So after the motor is done with its cycle and it pushes current back in the opposite direction, right? Or creates a voltage in the opposite direction, it's not going to damage the transistor. So what's going to happen is this: when the motor is done with its cycle, there's going to be a current that's going to flow, and that current is going to go back in this direction. So instead of it going back up here to the power supply or damaging something, it'll go through this shunt diode here, or called kickback diode. All right, so we just put this diode in the opposite direction. Use a normal silicon rectifier diode. Just put it in the opposite direction that current would normally flow. Because if you put the diode like this, right, it would just shunt past the motor. We don't want to do that. All right, so you put it in the opposite direction, right over the leads of the motor, and then that will protect it. All right, so let's go and go back and do that. Okay, so we've got our diode. We're going to use a 4001 silicon rectifier diode. This one's glass passivated. The cathode is over here on the right. So normally we would put the cathode, so current would flow into the anode, down the cathode to ground, but we're going to flip it around. All right, and we're going to put it just right across the motor itself, and here's the motor itself. So we're going to put cathode up here and put the anode right at the other end of the motor, and bear with me as I get this in here. Okay, there. So now what that's doing is that's protecting the transistor and the power supply from the motor's back EMF. All right, so now the motor will still work. All right, it's still pulling 1/3 of an amp. It's doing what it's supposed to do. Okay, so now let's go ahead. Let's use the motor for what the motor is for, which is pumping gas or air. So I've made this little balloon, this little diaphragm kind of thing, and we're just going to hook this up. And again, you know, this is kind of some fun mechatronic stuff. And this bladder here, you might, for example, the bladder, and we can just take this out here and just put it right here. You might, say for example, you wanted to move an object or lift an object. You could have a cylinder, and inside the cylinder you could have the bladder, and then you could have a platform, and then as this bladder fills up, it would push the platform up, and you could have a spring to pull it back down. So you could have something like that, and you could make something that this motor moves up and down without any gears, just by using air, or a pneumatic system, right? So a pneumatic system. All right, so let's go ahead, and I'm going to show you this, blow this up a little bit, and it's actually blowing it up. All right, now I want to show you something interesting, and if we can do this all at once here. All right, so what I'm going to do is I'm going to hold this in my right hand, and hopefully you can see everything. So I'm just going to turn this on, and I want you to see what happens to the current as I squeeze it. So I'm creating resistance, right? And that's going to have an effect on the system. So I'm going to turn this on. I'm going to talk a little bit loud to get over the motor hum. All right, so here we go. So now watch. See, as I hold it, look at that current go up. Okay, and the current goes up because the system's got to fight more. It's got to work more. All right. So, and then I'll let off of it, and then it goes back down to 0.3, and then I'll really squish it, and then I can get it to 0.33. So, you know, that's a poor man's, you know, how tight you could squeeze it measurement device. And then there's no way to gas this out, so we just have to open it up, or we could reverse it, right? We could reverse it, reverse the motor. So this, I think the second though I let this go, the motor is going to discharge. All right, so we're going to go here like this and reverse it. The diode stays in the same direction. The motor's just going to flip in the opposite direction now, right? Ideally. So let's see if that works, and it evacuates it. Yeah, no. So in this particular motor, there's a diode in there, bridge rectifier, that no matter which direction you power it in, even though it has a suggested positive and negative, it's always going to blow. So to evacuate it, we just have to pop it out. All right. So there's a little mechatronic system. So so the whole point is we use the transistor to control a load of almost, you know, 300 milliamps, you know, 0.3 amps. That's a lot of current, right? All with our transistor. Now, if we wanted more current control, right, we could use a bigger transistor, a different transistor that's designed for amps, right, and surely you can find that. But if you didn't have that, what you could do is you could put more than one transistor and actually put them in parallel. We could parallel the transistors together so that each could be a current leg, and then we could get even more current going through the system and more heat dissipating. All right, so that is that about wraps it up for using a transistor as a switch. So we saw how to use it at inverting mode, non-inverting mode. We showed how to kind of take an input, a 5-volt input, and turn it to an output. Then we showed how we could use this to control a large load, in this case a motor, a 1/3 of an amp motor. And then we talked a little bit about this little kickback diode here, which when you do motors and inductors, inductive loads, that is something to protect your circuitry. And we talked about the active and saturated mode. We're not going to really worry too much about the active mode of the transistor for our needs because we're going to use it kind of in a digital switch method. But you know that it's there and it can be used as an amplifier. But what we're going to use as amplifiers, if we ever need one, is an op amp instead of the transistor because it's just much easier to bias and get working. All right, so that about wraps it up for transistors, and I will see you in the next lecture. Bye-bye. All right, well, welcome back. We're on the next lecture, and we're going to be talking about MOSFETs in this lecture. So hopefully you've recovered from the transistor and diode lectures. It's kind of like the Hunger Games. That was pretty long and brutal. But we're almost to the end, and I wasn't going to cover MOSFETs, but I decided I wanted to add them in because typically when doing digital electronics, I would prefer if you use MOSFETs for switches and even for amplifiers. So it's kind of just a better tool to use than transistors for many, many reasons. Anyway, so what I want to do here is I want to explain how a MOSFET works. And so first the word or the term MOSFET, it stands for metal oxide semiconductor field effect transistor. And that is a big mouthful of words there. And so metal oxide semiconductor, it's kind of just talking about the materials that it's constructed of. So metal oxide semiconductor, and now the word MOSFET now is kind of it's kind of generalized to kind of refer to these kinds of transistors, even if they don't have oxides or metal, and if they're made of slightly different materials, you kind of just still call them MOSFETs. All right. So unlike the transistor, which is a device which is a current-controlled device, where we had P-type and N-type materials, we had them sandwiched together, and then we would inject a current into the base or draw a current out of the base, and then this would cause a secondary effect of current flowing through the entire transistor. And then we could use it as a switch or an amplifier. And we didn't learn all the more complex modeling equations, but we looked at the physics of what was going on. And so we were moving charge in and out of the base, and that's how we got the transistor action to function. The field effect transistor, and if we just analyze the words field effect transistor, transistor has nothing to do with a transistor. The field effect is kind of the key term here. And how this works is, so up here on the screen, you see a cross-section of an N-channel enhancement mode MOSFET. So just like the transistor, there are NPN and PNP transistors, there are N-channel and P-channel MOSFETs or FETs. There's also what are called depletion mode and enhancement mode. And enhancement mode is what we're going to be talking about. And after I talk about those, then I'll say what depletion mode is. There's also JFETs, which are junction field effect transistors. There are many, many, many kinds and variations of MOSFETs or field effect transistors, the same as there are for transistors. But typically, what we're going to be working with is N-type, N-channel, P-channel, enhancement mode, and actually we're kind of going to focus on N-channel for the analysis, and then we'll see how to use both N and P channel. They're just the opposite, just like the NPN transistor and the PNP transistor. All right, so let's take a look at this figure we have in front of us here. And so this is a cross section. So this would actually be what one of these transistors look like, these field effect transistors, if we were to look at the actual silicon. And so let's kind of see what we can do here. All right, so the first thing is we've got this metal gate right here. All right, and this is called the gate, and there's metal right here. That's where that metal comes from, metal oxide semiconductor. Then this hashed area, this is oxide, typically silicon dioxide, silicon oxide. It's an insulator, and but it could be something else. But the bottom line is it's an insulator, and it's really easy to grow when they make semiconductor transistors, because you already have the silicon and then you just add oxygen, you get silicon dioxide. All right, so that's an insulator. So the first thing is that we've got a metal gate which is going to go to this terminal called the gate, and then there's an insulator. So this is the first key element here. The gate, which is kind of like the base in a transistor, there's no current path from that into the device here. So it actually terminates at this metal gate. So in essence, what we're going to actually create is a capacitor. All right, so the field effect transistor operates on kind of a capacitive basis. So by the capacitor action of charges accumulating, positive and negative, we're going to create a set of conditions that are going to allow a current to flow. All right, so let's keep looking at this. All right, now the reason it's called N-channel is because in this particular case, we have a source, it's called, and this is going to be N-type material. All right, so this is silicon, it's been doped N-type. And then over here we have a drain, which has also been doped N-type. So we've got two N-type materials here. So that's where the N-channel is going to come from. Whatever the doping of the source and the drain, that's kind of what the channel is, N-channel or P-channel. All right. Then the source and the drain also actually have metal fused to them so that we can get signals in and out, right? So it's not shown in here, but there's actually metal. And if I have a gray, maybe a dark gray, we could kind of show that maybe let's use black. So we could think of there's some metal here, which is going to make contact with this drain, and similarly there's metal here. All right, and because we have to actually make an electrical contact, right? So there's metal there, there's metal there. All right, okay, so now we've got what we're calling the source, we've got the drain, we've got this metal gate right here, just this piece of metal, and then there's an insulator under it, and then we've got this thing called the gate. Now, then we have this thing called the substrate or body, and this is what this transistor is kind of all resting on and what it's kind of operating in. And this is doped P-type, okay? So we've got a P-type material, we've got these N, source and drain, we've got this P-type substrate or body, and then this other signal here is called the body, B for the body. And this is not exported out typically of a field effect transistor. You have the source, gate, and drain, just like you have the collector, emitter, and base. So we usually operate with just these three signals right here. Now, that's not completely true all the time. Sometime you will get this connection. You'll have a 4-pin transistor, field effect transistor. But for our purposes, this is just an illustration. Okay. So we have the substrate or body here, which is P-type. We've got source and drain, and now this thing is just sitting here. So what are some things that we know from semiconductor theory stuff, right? One thing we know is wherever there's a P and an N, we're going to start to get these depletion regions, right? So that's one thing. So let's get a color that draws well. So we're going to get some depletion region right here, right? So there's a depletion region right there. And of course, that's in 3D, right? That's going back, you know, like this and all that, right? So, and then if we can't see through that, right? So that's kind of what that would look like, right? And then the same thing over here, we're going to get a depletion region here. Okay. And of course, over here, this is a 3D object at this point. And actually it goes around here. And then this one goes around here too. Right? So you get the point. All right, so we've got those depletion regions there. All right, and so we've got something to overcome to get some current flow here no matter what. So that's one interesting effect of having the N and the P regions. All right, now, so let's just forget those exist because they're not going to be part of this analysis, but they are in there, and you do have to take those into consideration if you want to fully understand exactly how this device works, but we do not care about these for our analysis. All right, and we don't have enough undos. All right, well, let me put this back here a little bit so it doesn't look too asymmetrical. Okay, now, so what happens now is we're going to try and turn this thing on. So what we do is we apply a positive voltage to the gate. So we apply a positive voltage of V plus to the gate relative to this substrate or body. So we could just say that this is, we could think of this as being down at ground, right? Okay. And so we apply a positive voltage here. And what happens is when we apply this positive voltage, we basically have a capacitor. And so we start getting positive charge accumulation up here on the gate. So the gate becomes positively charged. As the gate becomes positively charged, then what happens is this P-type material, right, which is normally bulk P-type material, so overall it's positively charged. But what starts to happen is we start to drag and deform, if you will, this this material, and we start to create a negative area. So we actually create a net negative charge here. So this thing's like a capacitor. So we've got a field, and that's where the field effect comes in, right? So that's where the word field effect, and maybe we can draw this with a green or something. And so those field lines from the capacitor are kind of, going like that. We're creating a field. We've got positive charge accumulating here because we're putting a positive charge on the gate, which is causing a negative charge to get dragged up under the gate here. But because there's this insulation, this oxide here, no charge actually moves. There's no current flow, So that's super, super important. All right. So one thing is, and we can put it right here, 0 current flow through the gate. This is really, really important. 0 current flow through the gate. All right, current flow through the gate. All right, so now what we're doing is we're forward biasing this, okay? And just like we did the transistor, we are turning this thing on. And this is why it's called an enhancement mode MOSFET, for one thing, is that a positive, so the device is off normally, so it's off, and when to turn it on we use a positive voltage on the gate here, and that's enhancement mode. So, or if this was a P channel, then we would use a negative voltage, and either way, enhancement mode means we turn the thing on and rather than turn the thing off, so it's already off, and now we turn it on by applying this field here. All right, so now another little thing, another little detail is that the the source is typically connected to the substrate. Okay, so the source is typically connected to the substrate in a way. So you could think of the source is kind of connected here to the substrate. So because we need the substrate to have some kind of reference to ground or some reference as we put this positive voltage on here, otherwise it would be floating. All right, so the substrate is typically connected to the source, and then if we connect the source to some voltage source or potential, then we can kind of get this this relative voltage, the gate to source. So so what this is basically ends up being is we apply what's called VGS, voltage from gate to source. So VGS is the voltage that we're going to apply to the gate to the source. That's going to turn on this field, and as the field gets stronger, you're going to get more positive charge, you're going to get more negative charge here. And then now, here's where the cool part happens. So basically, we've got all these free electrons, in this case, right, in the N-channel device, just sitting here. But we have no current flow from the drain to the source because we haven't applied any voltage, right? So they're just sitting there waiting, right? So once this VGS gets sufficiently high, and that sufficiently high is when VGS is greater than something called V threshold, all right? And that threshold voltage, once it gets to that point right there, this transistor starts really turning on, and you'll get enough charge here so that you can get appreciable current flow from the source to the drain. Now, these look completely symmetrical, but remember, typically the source is connected to the body or the substrate, so that gives us a reference. So it becomes asymmetrical. So you could technically use the MOSFET in either direction, source, drain, drain, source, but because internally it's actually connected, now it actually has a polarity. All right, and then later when we see the symbols, you'll see that the symbols actually have a diode to remind you to not put it in that direction, to put it in the other direction. So in this case, the source is going to be connected to negative, and then the drain would be connected to positive. And you can think of it like this: since it's an N-channel device, the source would be the source of whatever the charge carriers are. In this case, the current carriers, and they're electrons, they're negative charge. So the source needs to go to something negative, and then the drain goes to something positive, all right? Now, so if we go ahead, and so we have this VGS here, which is a positive, all right? So let's kind of draw this a little bit here. So we'll draw it like this, and we will draw, go back like this. Okay. So there's our VGS, and that's some positive voltage, which is around or getting close to this thing called V threshold, which kind of really turns this thing on. And then the source to drain, what we want to have here is we want to have another power source. So the source, we could say, we can put this to ground, for example, and use that as a reference. Then on the drain, we put another positive voltage, and then that goes to ground also for a reference. And there's plus and minus. All right, and then there's plus and minus. So now what happens is, do we get any current flowing into the gate? The answer is no. There is no current. And that's one of the reasons why MOSFETs are so useful. There's no current to turn these things on. There's current movement, right? As this gate charges and discharges, it's actually a capacitor. So some current goes back and some current goes forward, but only in the transition is there current. Once it's stable and switched to one mode or another, then there's no more current, because it's just like a capacitor. So it just, the charge moves in, charge moves out, but there's not a constant current flow like the transistor, right? Okay, so now we kind of got this set up. And now we've got this voltage over here, which I'm going to call this V sub D, all right? Or it's sometimes called V sub DD, all right? But we're just going to call it V sub D, and because it's the voltage on the drain, and it's relative to ground, right? And ground on the source is to ground here, so we could call it VDS as well. It's drain to source voltage, right? That's reasonable to do. Okay, so now what's going to happen is this. We're actually going to get, and again, we can look at whichever charge carrier we want to look at, either electrons or holes, but what's going to happen is this, is we're going to get electrons moving from the source to the drain, all right? So these electrons are going to move from the source to the drain, and, you know, in this rightward direction here, and then, you know, go up and out the drain here. So kind of this situation here. So we've got electrons moving through here, and we've got a current flow. So we're going to have conventional current going in the opposite direction, right? So I'll just make that blue real quick. So we're going to have this current right here, which is going to go like this and down like this. Okay, and the blue current, we typically call this, I sub D, the drain current. Okay. So that's what's going to happen. Now, what I want to do is I want to kind of focus on, and let me see, I might have another figure. Yeah, that might be a little bit easier. I want to focus on, so now another thing is, because we're putting a voltage here from the drain to the source, this area in here between the drain and the source, these two N material regions, it's actually asymmetrical. So it doesn't open a channel that's a rectangle. It opens a channel that's a wedge. So it's wider at one end and smaller at another end, right? So what it actually looks like is, and I'm going to draw this. Why don't I draw this in black or pink? All right. So this channel actually is going to be this wedge. All right, and so as this voltage, drain to source voltage, gets larger, this wedge changes shape. All right, and also as the VGS, the gate to source voltage, it also gets larger as well. All right, so the point is we're using a field, an electric field, to modulate the amount of charge carriers in this region here, this P-type substrate, and we're kind of cheating the system. We're turning a P material into an N-type material and allowing current flow. So when you're all said and done with this thing follows some certain rules that are very similar to a transistor, well, analogous to a transistor, and we can use it both as a switch and as an amplifier. So let's take a look at some of that. So let me get rid of this. All right, and let's bring in another. Let's see here. Let me bring in. Let me see if I can bring this image here. And okay. All right. And okay, that's good enough. All right. So, and I cut this off a little bit. So up here, right? So this vertical graph is I sub D, and this is I sub D, and these are just in milliamperes. Now this is just a generic curve that describes what's going on here. And for every transistor, there'll be different curves and different voltages and different everything. But we just want to see, kind of get a feel for what this thing looks like. All right. So if you remember with the transistor, we had the characteristic curves, and they look something like this thing on the right. All right. And that's exactly what's going on here. All right. So the first thing is that the MOSFETs have 3 different operating regions, all right? And this is going to be a little bit confusing because they use similar names for the transistor and they do opposite things. All right, so there's what's called the ohmic region of operation, and that's also called the triode region. So let's see, let's put modes of operation. Modes of operation. Okay, so we've got this ohmic mode. Okay, we'll call that number 1. And then we've got one that's called saturation, and you're not going to like this. That's number 2. And then we've got another mode which is called cutoff or pinch off. All right, and that's going to be mode 3. The reason why you probably won't like the saturation mode is because saturation means the opposite of what it meant with the transistor. In the transistor, the saturation mode meant that the transistor was completely saturated, and you were pumping as much current through it. In the MOSFET, saturation mode is the mode where we want to operate the transistor, the MOSFET, for amplification. So in the linear mode in the transistors where we wanted to go for amplification. So anyway, you just need to write these down and just not get confused. They're confusing even talking about. But let's draw and see what's going on here. All right, so let me get a decent color here that kind of shows up good here. All right, so the first thing is, let's look at the graph on the left. I've never really liked these graphs right here, these characteristic curve graphs. They're just, they tell what's going on, but they're kind of confusing. All right, so the one on the left, though, this makes more sense. And what this is plotting VGS, so this is the gate to source voltage, and it's plotting this versus the drain current in milliamperes. So as we increase the gate to source voltage, we get more drain current. And it starts off very little, very little, very little. Then it looks like it's exponential, and then it looks like it's kind of linear, right? So in actuality, this curve is kind of a square curve. It follows a square law. All right. And then it gets linear in you know, up in this region here. Now it's never really linear. If you look at it, if you zoom in, it's always got a curve to it, right? Because it is a parabola. All right. But if we use it up in this region here, right, we can get a linear action out of it. And I'll show you that in a second. All right, so first, there's this VT. This is this V threshold, all right? And in this particular graph, which is just a generic N-channel MOSFET, it's saying that the threshold is 2 volts. So after 2 volts, this thing starts getting going, and you're going to start to get some current flow. So VGS is 1 volt, 1.5, and finally it gets to 2 volts, and this thing starts operating. The reason for that is the geometry of it, the construction of it, et cetera, and then what we're trying to do is with that field, we're trying to put positive charge up here and negative charge down here to try and allow enough free charge carriers so that we can get some current from the drain to source or source to drain, depending if you're talking about conventional or electron current. All right. Once we're up on this part of the curve, this is where the fun begins, because then look, we basically, you apply more voltage, you get more current, right? Okay, that's good. Now, let's take a look. Let's take a look at the one of the equations here. So one of the equations that model this states that I sub d equals k times, and it should be, yeah, VGS minus V threshold squared. All right, so this is the modeling equation, a simple version of the modeling equation. And the thing about semiconductors and FETs and transistors and all of this stuff, again, and I talked about this when we first started, electronics is basically the application of models to get the job done. And if we need to use a more complex model, then we need to use a more complex model. This model will suffice for what we're talking about, but if you need to be very accurate, then you need to use the model that takes other things into consideration. And these models can be a page long of math, right? But this will suffice. So I sub d equals k times the quantity VGS, which is whatever you have the current gate source voltage, minus this threshold squared. So this is really, really simple. So this is a beautiful, it's basically a square. It's just a parabola, right? And it starts off at dead zero. So that's really cool. The only question is, you know, what is this k? All right, and this k is a constant, and it depends on the width, length, various geometry, the doping of the transistor, and so forth. And where you find this k is inside of the data sheet for the transistor for the FET, if you wanted to use this equation. All right, so you find k and you can look it up inside of the data sheet, and then you can use this equation to compute what I sub d would be for some VGS. Okay, so that right there is one of our modeling equations. Now, and again, we don't know a lot about circuit analysis yet, so we can't do a lot of stuff, but when I get to that in a little bit, I'm going to show you a couple things that we'll be able to take advantage of, because remember, when we put the gate voltage on there to turn this thing on, there's no current flow. So that's really cool. So there's no current, so it's beautiful because we just have a gate voltage and we know exactly what it is. There's no voltage drops anywhere, so that kind of allows us to cheat and figure things out, which is kind of fun. All right. So let's talk about these regions here and kind of how we use this. And again, we just want to know how to use this. We're going to use it as a switch. We're not going to use it as an amplifier, so we don't need to worry about this too much, but let's just talk about this. So over here on the right, we have, and I'm going to overlay something here with my horrible writing. All right, so this is the saturation region, and this is the ohmic region. And then down here, when this thing is completely off, right, this is called the cutoff region. Okay, so, and then the difference between the ohmic and the saturation, it's basically where this curve ends and it flattens out, right? So just where the curve ends and it flattens out, that's all. So I just eyeballed it, right? So now once this thing starts flattening out, then we're in the saturation region. Okay. The saturation region is where this thing acts in an amplifier way, so we can use it as an amplifier. When it's in this ohmic region, you can see, again, we're following this curve. Basically, we're putting, in this case, this bottom of this graph is showing VDS. So as the drain source voltage changes, then we get current changing here. So basically, as the drain to source voltage changes, we get more current. So this thing's acting like a resistor, right? The bigger the voltage, the more current you get. It's actually acting like a resistor. And then the curve of each of one of those depends on what you're putting for the voltage from the gate to the source. So basically, in this ohmic region, that's why it's called ohmic, it acts like a voltage-controlled resistor. So you can actually change the resistance that it acts like with the gate to source voltage, and then whatever you put from drain to source, it will act like that resistor. So that's very useful, all right? But over here is where it's used as an amplifier. Okay, so once we get it into the saturation region, and so that means we have to, look at one of these curves, which one of these things, VGS 4 volts or 5 volts or 6 volts, we pick which one of these we want. Then we say as long as VDS is greater than whatever, as long as it's in the saturation side here, then we'll be in the saturation mode of operation, then we'll get the effect that we want, and that effect would be for amplification. And so what that maps to is this. So when we want to use this as an amplifier, what we do is this. We are going to bias this up just like we would the transistor, and we talked about using the transistor as an amplifier. We would bias it up, get it into this curve. Now, where do we want to put it in the curve? We don't want to put it here because this thing's all bendy, right? What we want to do, we don't want to put it down here. We want to put it into some place where it's in the middle of this, where it's very linear, right? And we've got a lot of headroom in both directions to go whichever way we need to with voltages. So just for kicks, we could say we're going to go right here. Okay, and then this would be kind of our bias point. So we would set VGS at, say, 6.5 volts, right? Then what's going to end up happening here is we're going to get an amplification. And forgive my lines. So we're going to set a DC, again, we're going to set a DC bias point, right? DC bias point or quiescent point. We're going to set this thing up. We're going to put it in the middle of this operating curve. Then what's going to happen is once we put it at that DC point, then we could put an AC signal on top of the DC signal, right? And so that would look, and you're going to see this kind of drawing, this kind of sideways drawing. You're going to put a small AC, so this is an AC signal, on top of the DC signal, right? Then what's going to happen is we're going to get out of here a larger signal, and it's going to be amplified. And so that's why we want to put this in the middle of this curve, so we have this headroom up and down to get this amplification. So that's when we use it as an amplifier, all right? And you can design these as using FETs as amplifiers, just like you can with transistors, and they've got really good properties. And typically, the majority of most amplifiers use FETs for the amplification process because of their properties of having extremely low on resistance and extremely fast switching time and low power because they have no base current, because they use a field effect instead of base current like a transistor does. Okay, so the takeaway here is we are going to use this thing in two different modes here. We are going to completely cut it off, and when we cut it off, it's just going to be like an open switch, and then we're going to completely blast this thing. We're going to put VGS so high, right? We're going to put VGS up into one of these curves up here. We're going to get the maximum amount of current, right? And if we want, we can push it in the ohmic or saturation region. It doesn't really matter. But typically, what happens is we do something like this, and this is kind of this load line, and we operate it at these two extremes. So cut off over here, and then completely on over here as a switch. Now, here's the cool part. The on resistance of these field effect transistors, which is called RDS, okay? And this is the drain to source resistance when it's on, can be on the order of milliohms, all right? And actually even microohms, all right? But you're going to see milliohm things. So if you, you know, typical might be 50 to 100 milliohms. In other words, when you turn this thing on hard, it literally acts like a short. This is a short. So you can get a ton of current through here. Moreover, because it's got such small resistance, there's no power dissipation, right? What does a 0 ohm resistor dissipate? Let's do the math real quick. If you can recall, and hopefully this hasn't been occluded the entire time. If you can recall, uh, if we take Ohm's law, we have V equals I times R, right? And then we learned that power equals voltage times current. We also learned that if we want to, we can replace, say, I. So I is V over R, right? So this also equals V times V over R, which equals V squared over R. All right. So V squared over R is one way we can compute power, right? Okay. Uh, Now, so and another way we could do it also is we could put things in terms of R's also for this RDS on. All right, but the bottom line is whatever the voltage drop is over the resistive element here, whatever the voltage drop is over the resistive element, that is going to get squared, whatever that voltage drop is over this resistor, and that's going to be the power. So we want that to be very, very, very small. So if we have these very small resistances, right, it doesn't matter what the current is, we're just like going to get nothing out of this thing. So like if we have something that's 25 milliohms, right, 25 milliohms, 25 times 10 to the minus 3 milliohms, right, for the resistor, uh, we're going to have very, very little power loss over it. So we can put amps through here. So for example, if we said that, and so if we wanted to compute, so let's do, for example, let's get our calculator. Let's say that we have a FET and we're going to put, let's say, 5 amps of current is going to flow through this. Okay, so let's say that ID is 5 amps of current. Let's say that we have an on resistance, RDS on, of 25 milliohms. So RDS on is 25 milliohms. Okay. All right, and we want to compute what this power is. All right, so we need V times I. All right, so we need V times I. Well, we have I and we have R. All right, so we can compute what this V is here. All right, so we know that the V over this is basically this current times this resistance, right? So that's 5 amps times 25 milliohms. All right, and so that voltage is 0.125 volts. All right, and so then we can take that 125 volts and we can just multiply it again times the current if we want. And we just, you know, do any permutation of this you like, but we'll just take that voltage, multiply it times the current again, times 5, and the power. So that's 0.625 watts. So not even 3/4 of a watt, not even 1 watt. So we're pumping 5 amps through here, right? And because the resistance is so small, we're barely dissipating, you know, 3/4 of a watt. That is a lot of current to only be dissipating 3/4 of a watt. So that means that these parts can be very, very, very small, and they are. That's what, you know, your Intel i7 is made out of, you know, a billion MOSFETs, like literally a billion or 2 billion, I think it's up to now. All right. So, so anyway, that is one of the reasons why we like MOSFETs. They have very, very low on resistance. They switch very, very fast, and you can move around enormous amounts of current with them. Okay. All right. So those are the graphs and all that. So let's see here. Let's go, and I think let's take a look at drawing some circuits with these and what these things look like here. All right. So one thing I want to show you that you're probably not going to like either is, because I don't like it, is that there are lots of different symbols used for the FETs, all right, and there's a P channel. And so the problem is this was never, there was never really a convention. So with the transistor is pretty easy, right? You remember? So here is a NPN, right? And then here is a PNP. So the arrow, right? So the arrow goes out in one case, and then the arrow goes in with the PNP. All right, so that's pretty easy. And then, you know, people, they decorate them, they put circles around them and play with them a little bit and put little lines on them and stuff. But these are pretty easy to draw, and everyone can kind of draw these, right? But when it comes to FETs, it's like you can find a million different, I'm exaggerating, you can find many, many different ways of drawing them. So we're talking about N channel first, and like I said, P channel is the same, just everything is opposite. So typically how these things will be drawn is something like this. You'll have, and let's use a dark red here to kind of go over this. So you'll have the gate, and the gate will have this kind of L shape here, usually. All right, and then this one is the substrate connection right here. All right, if it shows it. All right, but let's just forget about that for now. All right, so typically we'll be using this one and this one. And so we've got the gate, then we've got the drain, then we've got the source. So the first thing you do is you draw this L shape, and then you draw three little lines. Then the L shape always points down kind of to the source. All right, so it always points down to the source when you're drawing this, all right? So that's one thing. Then you got these three little lines. Then the drain is easy. You just draw a line, there's a drain. Okay, but then you need to draw this source. So then you take the next two connections and you connect them together, and then you draw an arrow pointing inward if it's going to be N channel, or an arrow pointing outward if it's going to be P channel. All right. Then the other thing that you will see, is you will see diodes in the drawings. And do I have the? Yeah, I actually do have this. I actually do have this for you, but we'll just do it here. I had a nice figure for you. All right. And these diodes aren't actually here, but they're intrinsic because of the design of the MOSFET. And what this shows you is, you know, you don't want to let current flow this way. So don't hook it up in this direction, hook it up in the other direction against this diodes, because conventional current is going to flow like this. All right. So in this case, conventional current will flow like this, and then conventional current flows like this. So you may see them with these diodes, and those are just little helpers to help you kind of see. Don't hook it up in that direction. Conventional current's going to go down, or conventional current is going to go up against the direction of the diode. So it's going to go against the direction of the diode. So that's the way that you want to set this thing up. So other than that, it's kind of like a transistor. So this is kind of like the base, right? This is kind of like the collector, right? And then this is kind of like the emitter, kinda. All right. And so so that's what they look like. All right, so we know the model of it. The ID equals K times quantity VGS minus V threshold quantity squared. We know the symbol for it. We know that there's an N version and a P version, right? The only difference with the P version is, instead of applying a positive voltage between the gate and the source, we apply a negative voltage, right? And then we get it a channel that, instead of electrons, are holes are the majority carrier, right? Everything is backwards, and then everything is backwards, all right? So, and we're going to actually do a circuit with these both, and so you can see them actually in action. But we understand the physics of the N channel, and the P channel is exactly the same, just everything's backwards, okay? All right, so I think we're ready. I'm just looking over here at my notes if there's anything else. Okay, so I think we're ready to go ahead and start building some circuits with this thing and taking a look at some stuff, all right? So, so let's go ahead and let's go over to the bench camera, and let's build some circuits, all right? So before we do that, we're going to go over and just take a quick look at what these things look like, because they look just like transistors. And then we're going to come back and draw something on the computer here, and then we're going to go build it, and then build a couple variations like we did the transistors. Not as much stuff, but enough so you can see these things being used as switches, all right? So, go ahead, and we're going to meet over at the bench camera here and keep going, all right? Okay, so we are back here at the bench camera, and we're just going to take a look at some couple FETs here. And now, unfortunately, most of the FETs that I use are all surface mount, so I don't have a lot of through-hole FETs unless they're big power FETs. So we'll look on the computer for some, but I just want to show you some of these packages so you can kind of take a look at them. So first thing here is let's take a look at this one under the zoomed camera. So this is a TO92 package, and this is one package that you'll find FETs in. Now this is actually a transistor. This is a 3906 transistor, but this is a popular package for FETs, and I wanted to show you that. So this is the TO92 package, all right? Now, here I have a couple surface mount FETs. And again, because they can be so small, because of their low on resistance, you're going to find a lot of these in surface mount now. Now this is a FDC 606. This is a P-channel FET, and it's in this package right here, which is this is a, I believe it's called a SOT23 or an SOT6. In any event, it has 6 leads. So what's going on with this? Well, because it can carry so much current, it has more than one lead that's the same. In this case, it's got drain, 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 gate, and source. So more than one pin has the same function. They're all electrically tied internally to the same thing. And that way you can get more current flow, all right, instead of just going through a couple little pins, all right? And here's another field effect transistor. This one is a FDV 305, and this is an N-channel FET like we were looking at. And again, very small. And this is an SOT 23, it's called. And again, you have to solder them on these little boards so that you can experiment with them, and you can see source, drain, and gate. All right. So there's those packages, and there's just many packages when they come small and surface mount. Now, I wanted to show you this. So here is, this is an N-channel, this is an IRF 7030, and again, I'm saying these as if they're very specific. They're not. There are tens of thousands of FETs and transistors. In fact, I think there's about 120,000 different transistors on DigiKey and about 70,000 different FETs. So there are countless. So really, when you want to use these things, you have to go into the data sheets, you have to go through the search engine on DigiKey or Mouser or wherever you would like to buy your parts, put the parameters in that you're looking for the performance characteristics you're looking for, the price, and then start looking at the parts and downloading data sheets and reading. And then over time, you start to use certain parts and they become kind of your go-to part. And that happened with the 3904 and the 3906 from the transistor world. But in the FET world, it hasn't happened as much. There's no clear, your go-to N-channel and P-channel FET. So I'll talk about a couple that are sort of the go-to, but just not really. Anyway, so here's how some things come. So this is this package right here, and you can see right on here, bring it in if it stays in focus, is a TO220 package. And these are really big, and they can dissipate a lot of heat. All right, so that's what that looks like. And if we look at the data sheet and the specs of it, this one's a 400 volt, 5.5 amp N-channel MOSFET. Let's look at it on the zoomed in screen. So we can see that there. All right, and you can see the part numbers right on there. All right, and then now, so this is interesting. So this thing, you haven't seen this before. This is a heat sink. And so after you solder this into your board, and typically these pins would be bent. So they would be bent at a right angle. And then there would be a hole in the board, the PCB. This would be mounted onto the board, typically soldered onto the board. And then a screw would go down into it. Now, if it's not soldered and it's just mechanically held there, there will be conductive grease, thermal grease on there. And then that'll make a good contact, and then you'll screw this down, and then the heat will dissipate into this metal tab and then into the printed circuit board so they can get rid of that heat because it's going to be dissipating a lot because this is a 5 amp FET, for example, right? Okay, so that's kind of what they look like. Today we're going to be using these guys for our experiments, all right? So just pretend that they're through hole. And they're just mounted on these little adapter boards, these little breakout adapter boards, which many companies make them. If you type in SMT or surface mount 2 dip adapter. You can find many companies that make these, and in the section 1 in all our resources, there's a list of actual websites that you can get these adapters, and they're very expensive, as I mentioned before. All right, so let's go ahead and we'll just put this away. And then, one thing is, excuse me, one thing is when you're messing around with this stuff, you want to put things away and put them back and keep track of them, or you just lose everything. And then, and I had one more I wanted to show you here. So if you can read that, this is an FDA 69N25, and this is a MOSFET 250 volt, and this is 69 amps, 70 amps of current this bad boy can flow. So let's take a look. I haven't even opened this up. This is for a power project one time, and I didn't need to use them, I guess. I must have used something else, or I didn't use all of them and I had more packages of them. So look at those. How awesome is that? 70 amps each, basically. So let's take that out and take a look at it. And this package is called a TO3P. And again, there's countless packages also. These companies, practically make these things up, and so you'll just find package after package. Let's look at that under the zoom camera. So there it is right there, FDA 69N25. That is pretty awesome, huh? Look at that heat sink. So, that level of FET you could use for big motor control, so you could, 70 amp, this could be for an electric, a small electric car, a motorcycle, something of that nature, and you could control it with this. All right, so very, very cool part. And, they make these things that can, tolerate 1,000 amps, if you can believe that. All right, so let's go ahead and put this away. Fun. And let's go back to the computer and let's start drawing some circuitry here, and then we'll come back and start building stuff. So you can see this little thing here. I'm not going to tell you what that is yet until we go over to the computer and start drawing some circuits. So let's draw our first circuit and let's get right back here. First, we're on the computer here. You can see we've got this 2N7000. So this is an N-channel enhancement mode MOSFET. One of the most, kind of popular go-to MOSFETs for hobbyists. And let me get up its data sheet here. And you can see it's got the TO92 package and then like an SOT23 like you saw of the other package. All right, you can see the symbol here, gate, remember it's that little L. And then we've got the 3 little flat little feet thing here, feet things, and then we've got the arrow pointing in. All right, and then these are connected together, and then we have this diode, this body diode here to remind us that there's a diode there, so you don't want to forward bias that. So you want to make sure that current flows in this direction and downward direction. Okay, so anyway, so the 2700 2N7000, and this is a good, all around get the job done, and it comes in a TO92. And let's see, let's look for its RDS on. Remember we talked about that, so let's just look for RDS. All right, and this is the static drain source on resistance. And so this is going to be at different, and again, with these data sheets, you got to bear with them because some manufacturers put information that's useful, some put that's not useful, and they put it all over the place, and you got to take your time and go through it. So this is saying at VGS equals 10 volts, ID equals 500 milliamperes, and then we're showing a number of different transistor variations. The one we're looking at is the 2N7000. And then it's saying what the typical on resistance is here. So if we're at 10 volts, then we're getting about 2 ohms of on resistance. If we're at half of that, 4.5 volts, and we have less current, then we're getting these values here. All right, and then so forth. And you just kind of read through here, and it's always partial information, and it's half right and half, missing and all that as you go through these data sheets, and it's always the same. And then of course we've got the various curves here that show, like for example, this one is the I sub D as a function of VDS, and those are like those characteristic curves that we looked at with the other drawings and so forth. Anyway, this would be a good field effect transistor for you to pick up some of. So 2N7000, get 10 of them, get 20 of them, and then you can play with these things. and they go 400 milliamperes. You can probably do 500 milliamperes fine, and they'll go to 2 amps pulsed. All right, so there's one right there. And so that's an N-channel enhancement mode. Then another one, let's see here, that I like for you that has a TO92 package is this BS170, which is very similar to the 2N7000. And again, same thing. And now you got a slightly different symbol here. Drew it a little bit different way, right? The voltage stuff is the same, but now you can see here the continuous current on this one's a little bit higher. So this one is 500 milliamps, right? And then the pulse current is a little bit less. This one's 1200 milliamps instead of the 2 amps of the one we were just looking at, right? And so anyway, so this is another good one. So you could get either one. Me personally, I would just get both so you could play with them and have extra units. Okay, and let's see, what else do we want to take a look at here? Let's take a look at, all right, and here, the transistor that we're going to use for our experiments, we have an N channel, which is this FDV 305N. This is an N-channel power trench MOSFET, and that's just a marketing word and a registered trademark, and it's a certain kind of construction technique that they use to make the MOSFET. Anyway, you can see here, here's the labelings of things, but what I want to bring your attention to here is this. At a 2.5 volt VGS, we've got 300 milliohms only of RDS on. That's pretty good. And then at 4.5, if we increase that even more, it drops down to 220 milliohms, right? And now what we're really looking for is 0 milliohms, right? That would be ideal. But to get that, it's more money. However, if we go over to, let's see, and I want to see what else we got here. And I've just picked a few for you here. That was the one we were looking at, that big one, right? That IRF 710, we were looking at that, the 220 package one, right? And so this is another power MOSFET. But if you wanted to get a power MOSFET, what I would probably suggest is this one, the IRF 510. And this one here, it's got an RDS on of 0.54 ohms at a VGS of 10 volts, and it can handle 100 volts from VDS. This other one, this IRF 710, what's good about it is it can handle 400 volts, but it's got a much higher RDS on, but it can handle a much larger voltage. And that makes sense. If you think about it, how's it handling that large voltage? Well, it's got, the silicon is larger, the geometry is bigger, so it can handle larger fields, larger currents, and because of that, it's just going to probably have more resistance. It's going to take more work to move charge through it because it's just bulkier and bigger, and of course that's why the RDS on is different. But if you need that, then there you go. So if you're going to be playing with big motors, any of these IRF series, 510, 710, 500, 700 series, just look at them, read all the data sheets, and these will do what you need to do. All right, and let's see here. Let's look up another one. Let's actually use the tool here. So, oh yeah, I was looking, and there are 67,666 different MOSFETs here. So FDC 606, this is from Fairchild. This is one of my favorite. This FDC 600 series from Fairchild, and they have both N channel and P channel. And what I like about these are logic level gates, meaning these things can be turned on and used as a switch just with logic level VGSs, and this one is 1.8 volts. However, look at the drain to source voltage. So they can only withstand like 12 volts, right? So you can't put a lot of voltage across the drain to the source. But look at these RDS ons, 26 milliohms. That's crazy. Very cool. So, and then here's the data sheet for it. Just pop that up and open this up a little bit for you so you can see it. And there we go again and again. You can see there's drain, 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 source, gate. It doesn't have multiple drains. They're just electrically connected together in the package. That's all. So they could put it in the larger package so it could dissipate more heat as a surface mount device, and you get some more current pass going into those ports or leads on the actual device inside of the package. All right. And now look at this one right here. Look how crazy this is. 6 amps. This thing can flow 6 amps. All right. Now, one thing you're going to notice, and I don't want to get too hung up on this right now, is when you are looking at parameters for N channel and P channel, as a convention, they'll use negative numbers on the P channel devices. And so VGS is minus 4.5 because we have to use a negative voltage to turn these things on. So these negatives, it's not really flowing negative 6 amps, right? Current is positive or negative just depending on which way you want to use as your convention. So it's not like uh, sucking current out of something. It's still flowing 6 amps. It's just saying that because of the convention of how they like to make these data sheets, they just say it's minus 6 amps. That's all. So don't get hung up on that. Don't get all crazy and think there's something weird going on. So we're going to use this one and the other one, where to go, this one here, and we're going to use this in our circuits that we're going to hook things up. So we're going to ignore kind of what they look like in their package, and we're going to use them in the abstract. All right, so let's start off. Why don't we start off with the N channel, and let's draw a circuit with that. So let's go over here, okay, and let's get on our drawing thing here. All right, and let's go ahead and, so N channel, let's pick orange. Okay, so first we got to draw our field effect transistor. Okay, all right, and we'll draw our three little guys here, like so. And I'm going to be honest with you. It's like I've been drawing transistors so long. You get to the point where, let me show you how I really draw one of these transistors. That's it. I'm done. That's it. I don't even get into all this other stuff, but you'll just, after a while, you'll start to get very, very lazy, and you just don't care anymore. All right, there's that, but we want to draw these correct since we're learning it. All right, and then we want our arrow in here. Okay, so that is my rendition. All right, and that's the gate, and that's the drain, and that's the source. All right. Okay, so, and we can put little circles here. All right, and let's say what this again is. This is an N channel. All right, and then we'll say E mode for enhancement mode. Just means that a positive voltage is going to turn it on and it's already off. It just means it's off and we turn it on. Enhancement, if it's depletion mode, it's already on and we turn it off. N channel, E mode MOSFET. Okay, and all I want to do is use this thing as a switch. I just want to use this thing as a switch. Okay, so what we're going to do in this is when you have an N channel device, we're going to use it as a switch, and we're going to basically connect the source directly to ground, like that. All right, we're going to connect that to ground, and on our gate here, we're going to apply some voltage, so we'll get to that in a second. Now on the drain right here, we're going to connect our load. All right, and for now, I'm just going to represent the load like this. And then here, this is going to go up to we're just going to call this, this is not V sub D. This is going to be V sub, we're going to call this V sub CC. In our case, we're going to set this actually equal to 5 volts. Okay, we're going to set this equal to 5 volts. All right, so now this right here at this node, right there at that node, that would be V sub D. And then here at this node right here, this would be V sub S, which is equivalent to ground. And then here at this node right here, this would be V sub G, but since it's relative to ground, it's V sub GS also. All right, so it's right there. Okay, so now we want to use this thing as a switch. We have to apply a positive voltage between VGS. So our goal is to get VGS greater than V threshold. All right, that's number one thing that we want to do. And then the other thing that we want to do, if you remember those graphs, we want to push this thing all the way so that VDS is equal to nearly 0. So on the graph, there's the cutoff point at one end, and then up at the other point of the graph, there's the point where VDS is almost 0. We don't want anything to drop over this MOSFET. We just want it to be absolutely 0, just like a dead short. So what we're going to do is we're going to drive VGS really, really, really hard. So we're going to drive it all the way up to the 5 volts. Okay, so what we're going to do is we're going to put a switch here, like this, momentary switch. And then we're going to take this and we're going to connect this directly up to 5 volts, like that. All right, and so when we put this 5 volts on here, this is going to turn this thing on. All right, once it's on, VDS is going to go down to 0. I sub D is going to go to its maximum amount that it'll flow. RDS will go almost to zero, right? The resistance in this junction, and then we're going to get a current flow right here, right? And we're going to get a current flow like this to ground, and that's going to be I sub D, and that's going to be basically this resistor right here, this resistance, this RDS on, will become nominal, and whatever the load resistance is will dictate what the actual current will flow. Now, one more thing. When this MOSFET is just sitting here, to turn this on, we have to put a positive voltage. VGS has to be greater than V threshold, which is a positive voltage. However, when there's nothing on the gate, it's just floating around. We don't want it to float. We want to do something with it, right? So we don't want it to float, so we want to put a voltage on it so we know it's stable. So what we're going to do is we are going to take a resistor, and we're going to put it down to ground, and we're going to call this, how about we can call this R off. And all this is going to do is create a voltage, because no current is going to flow. No current is going to flow, right? Because remember, no current flows into the gate. It's just like a capacitor. So we can make this very, very large, all right? But we don't want to make it so large that other disturbances can modulate it too much. So you want to make it stiff enough, is the word, so that if something else comes on here, it can overtake that. If noise comes on this, it'll maintain this zero, all right? And then only when we put this full 5 volts, then we're going to get 5 volts here. But then what happens is we complete the circuit in two ways. When we close this 5 volt, then we're going to get current flow down through this resistor. We're going to get 5 volts at this node, but then we're going to get current flow. So if we make the resistor too small, making the circuit really nice and stiff, we're going to burn a lot of current when we turn this thing on by pulling it high. So we got to balance that, right? So let's just set this for a nice number is 10K, okay? 1K to 10K is what you want to use for your pull-up and pull-down resistors. Anything higher than 10K, it's just too weak of a pull-up or pull-down. Yeah, you may even get away with 22K, maybe 47K, but I wouldn't do that. 22K is kind of my limit, and I like to stay around 1 to 10K for pull-up and pull-down resistors, which is something you probably just heard the first time, but it's when we want to put a weak signal on something to make it stable, and then we're going to put a different signal on it, a really strong signal at other times, but we want it to be stable. Okay, so let's look at our circuit. When this thing is off, when VGS is 0, and VGS is going to be 0 when the switch is not depressed. VGS is 0, it's less than the threshold voltage, the MOSFET is completely off, there's going to be no current, there's going to be no I sub D, and then therefore there's going to be no current through here, and then this load is not going to do anything, right? It's just going to stay off. Now, we press this momentary switch. The moment we do that, now we've got 5 volts. 5 volts is right here. We're actually going to get a current flow down here. What are we going to get? What are we going to get? We get V equals I times R. In this case right here, so we want to compute I. So I equals V, which is what? 5 volts over R, which is 10K. All right, get out your calculator, right? What would that be? So 5 volts divided by the 10K, right? If it was 5 volts divided by 1K, what would it be? Think about that for a second and see if you can start to do these in your head. And and the answer is 0.5 milliamps, of course, or 500 microamps, okay? All right, so not a lot of current, but if you're doing a battery-powered something, this might be a lot of current, right? So then that's going to be on, whenever the switch is closed, we're going to get that current through here and burn a little bit of current. All right, then we're going to get a massive current when this thing gets turned on, a massive current through here, which is going to be dictated primarily by the load resistance, because this on resistance here, this RDS is very, very, very small. It's on the order of milliohms, right? 50, 200 milliohms, all right? So let's build this circuit. So all we need to do is take our load, and we're going to take our load with our N channel, and we're going to take our load through our MOSFET from drain to source to ground, and then on the gate we're going to take a 10K to ground, and then we're going to put a momentary switch, and then we're going to turn this thing on and we're going to turn this thing off, right? So let's go over to our bench camera and let's build this, okay? Okay, so let's do this. All right, so the first thing we need is our transistor, and we decided we're going to use the N channel first, so we're going to use this FDV305 NFET, N channel FET. So let me zoom in as usual here a little bit so you can see things. All right, and then I've got my hookup wires. I got my long ones, got my short ones. I got a bunch of resistors. I got a couple switches here. I've got my meters over here. I got everything that I need. Okay, so first thing is let's go ahead and let's place this into the board. All right, place this someplace here. So we'll put it right here. Okay, and then we said we're going to take the source is going to end up going to ground. And remember, since this is an N channel, it's the source of what? Electrons, and that's why it goes to ground. That's where our electrons are coming from, the negative. So we're going to hook this to ground. And let me make sure power's off here. Yep. All right, so the power's off, and then I'm going to show you something else I built, but right now we're going to just hook it up. So now we've got our load, and here's our load right here, and it's a coil of wire, right? It's a coil of wire. So let me show that to you on the zoomed camera. So it's a coil of wire. Can you see that? There you go. It's a coil of wire, and I made that coil of wire, and it's like this coil of wire, and this is made out of nichrome wire. All right, nichrome. And I don't know if you've ever heard of that, nickel chromium wire. And it's a type of wire that heats up, and it's the basis of many, many heating elements, all right, is nichrome. And so what we have here is you can get these spools of this wire, and this one is from this company called Wiretron, and I bought probably, I don't know, 50 different alloys I use for different kinds of heating element construction. But anyway, this is copper nickel 294, right? And so anyway, nichrome is a nickel chromium wire, and there's countless alloys that you can use for heating things. So anyway, this is actually nichrome, the big, thicker one here that I made. It's just too big, I can't heat it up enough with the current from our power supply. But this right here, this copper nickel 294, I can heat up enough, and we can actually get this to turn red if we can put enough current through it. Now, what I was going to do was just do another experiment and then do a motor, power a motor, right? But we kind of did that in the last one twice, so I thought let's do something that requires even more current. So this is going to take at least an amp to turn this red hot, an amp to turn it red hot. If you remember the previous thing, I think we did 200 milliamps, 300 milliamps. Now we're going to go for an amp with the MOSFET instead of the transistor. So let's see if our MOSFET can get us this power level that we want, which is an amp through here. Now, this particular one I think will flow a couple amps. We'd have to look back at the data sheet. I think it's 2.5 or 3 amps, and then the other P channel can do I think 5 or 6 amps. All right, so let's keep doing our circuit. So what do we need? We need to go from the positive, so V sub CC, which is going to be up here. All right, and that's going to be, we're going to just set it at 5 volts. All right, now we've gone through our load. All right, and now we're connecting the other end of the load to the drain. All right, and now this is called a low side configuration, low side. And the reason why it's low side is the load is up here high, then the switch is down here low. So it's low side. The switch is switching down here low. And so you'll typically use N channel FETs in low side, and then P channel FETs up at high side. The switch will be up high, and then the load will be down low. All right, and that's where that comes from. Okay, that's all we need there. And then on our gate, we need to take our gate, and we are going to pull that down low through a 10K. So what's 10K? Brown, black, orange. Brown, black, orange. There it is right there, brown, black, orange. Okay, and we're going to put that right here to the gate. Okay, and let's zoom in a little bit more, a little bit more. All right, so there we go. So you can see that's into the gate. Okay, source drain gate. Okay, and then now let's take a switch. And what do you think here? White switch, blue switch? Let's do a blue switch. So here's a blue switch. And we want to take this, and this is going to give us our plus 5 volts. So we're going to drive VGS all the way up to 5 volts, right? So we just need a wire here. Let's find one that'll reach. That's not too long and gangly. Yeah, this one will. All right, so kind of bend that up, get that going here. And then, you know, you got to pull these things up and see what's what. You got to wear your glasses or your magnifying lenses or work under magnification. Like some people, what they do is they just put one of those big magnifying lenses and they work through that, right? So either way, just, you know, don't strain your eyes. If you're going to start doing electronics in 20 years, you'll be blind. So don't push it. Now the other end of this is going to go also to the gate. All right, and again, let me get a piece of wire here. All right, this one's a little bit long, but it's just going to have to do. A little bit long. We're going to put this right to the gate. Okay. Okay. All right. Now, when I turn this power on of the power supply, and we've got it set for 5 volts, we should see nothing. Nothing should be on because we've got this thing pulled low. So VGS is 0 right now. Okay, so I'm going to turn it on. All right. And everything's good. 0 volts like we expect. Let's check it. Let's get out a meter, right? And I know we're going to do a lot of things that are obvious and simple, but you know, that's why 747 pilots have a checklist. They go through the checklist and then they know what is going on, and that way that there's no human error ideally. Okay, so let's put this into voltage mode. All right, so let's check our voltage here. Okay, so we're looking at the voltage on the gate, which is right here at this resistor, and sure enough, the voltage is 0. All right, so the voltage is 0 right now. What's the voltage from the drain to the source? Drain to the source, what's the voltage? All right, you got your answer? So let's take a look. So drain to source, these two guys right here, all right, on the left here. And I'm going to get in here so you can see it. I'm going to put a ground at source since it's already at ground. I'm going to go to drain. It's 5 volts. Right? It's 5 volts, and that's exactly what it should be. There's no current flowing through here. When this thing is on, that drain to source will go to 0, right? Because this MOSFET is going to have 0 resistance when this thing is fully on, right? It's going to be flowing a ton of current, okay? All right, so everything's good. So now what we're going to do is I'm going to actually turn this thing on, and when I do, this coil is going to get red hot. Now, just a little bit of mechanical stuff here. So what I did is I coiled this, I suspended it up on these 2 posts. We got this plastic, and then the 2 posts are going into here. This is going to get a bit hot, probably, I don't know, 150, 200 degrees maybe. It should be okay. It's not going to melt this plastic, but I'm not going to hold it on here for hours, right? Because it will sooner or later melt the plastic. All right, let's zoom in. Here we go. Zoom in, zoom in, zoom in. All right, and there we go. And now I'm going to turn off some light here. All right, and hopefully you can see this. And here we go. We're going to turn this on, and let's see if you can see it. And there we go. Can you see it turning red? How cool is that? And the power supply is showing 1 amp right now is going through it. And then I'll let it off. And I'll turn it back on. And I'll turn it back off. All right. And I already burnt my finger during when I was, checking this and testing this. I touched it there accidentally. All right, let's turn the light back on. Let's put an ammeter in here so we can measure the current and make sure we're getting what we think we're getting. So we'll take this meter, we'll put it into amp mode. We'll get one of our little connectors. All right, and then why don't we just put it, we'll put it right here in this leg. Okay, so go right here. Oops, careful, don't want to damage that coil. That wasn't easy to wrap. Careful, careful. Okay, trying to keep this all on the camera. All right, and we'll put our amp meter in there, and then we'll connect our leads here. All right, that's number 1. And while we're at it, let's also, why don't we measure the voltage from the drain to the source? Now, since the source is at ground, really, if we just measure drain to ground, that's the same as drain to source. So let's watch that go to 0. So let's get another meter. So I'm going to get another meter out here. All right, got another meter. And let's get another connector. So here we go here. And let's get this voltage. So here's the drain. And let's get a long wire. Here we go. So here's the drain right here. And there's the drain there. And remember, we don't have to take the drain right from the IC because there's a wire there. So electrically, this is all connected the same, yeah? All right, so now we got that. And now let's get to a ground. So here's a ground. Okay. And, okay, I just bent this up really bad. Now I'm mad at it. So guess what? It's done. Move it away. All right, let's try this. Ah, that went in nice. You know what? If things don't want to work with you, don't work with them. All right, now we're going to go in there. Let's get our voltmeter set up here. Put it on voltage. And I'll bring this into view in 1 second. I'm going to ground one end, put positive in the other end here. Okay, all right, now we're going to Bring all these things in close, and we're going to see what happens. Okay, we're going to zoom this camera back out here 1 second. Let me get these cables so they sit still. All right, move this up. Okay, so the meter on the left is current, the meter on the right is voltage, and as you would expect, right now there's no current, and the voltage across from drain to source is 5. When we turn this thing on, this should go to 0, and this should go to the maximum value of about an amp. Ready? And is the power on in the power supply? Yes, it is. And here we go. There's 1 amp and 240 millivolts. And the coil's on. Let me turn off the light. There you go. Let me move this so you can see it. There we go. All right. And it's not a special effect. Watch this. So I will take this is a piece of napkin, all right, and I'm going to take a little teeny tiny bit of alcohol. This is alcohol right here for cleaning, for soldering. We're just going to put a little bit of alcohol in here. If we can get it, there we go, a little bit of alcohol. All right,